Hey team, welcome to this complete course on Docker and containers. My goal with this course is for it to be the most efficient way for you to ramp up on your Docker and container skills, starting from the basics and progressing through to intermediate and advanced concepts. By the end of the course, you'll have the knowledge and skills to be productive within a team using containers for both development and deployment of their applications. You'll understand why you would want to use containers, as well as how to integrate them seamlessly into your own workflow. This course is split between theory and practice. For each section, I'll cover the concepts that you need to know using helpful visuals and diagrams before diving into our code editor and solidifying that knowledge with real-world examples. I've provided a companion GitHub repo linked in the description containing all of the code and configuration that will be shown throughout the course. Feel free to clone or fork the repo to follow along as we go. Before diving in, I do want to highlight a couple of prerequisites that will help you get the most out of this course. As the image shows, it can be tempting to jump straight into learning about containers and skipping some of the foundational concepts that they build upon. I'll do my best to explain everything in such a way that even an absolute beginner would understand, but if you have some familiarity with web application development and how all the different components fit together, that will be helpful and make it easier to understand what aspects are container specific and what aspects are just general application architecture concerns. Also, having some understanding of basics Linux shell commands will be useful, as we'll use such commands throughout the course. If you don't have these, I think you can still get value from the course, but some things that I do or say might not make sense, so it could be worthwhile to go and brush up on those topics first. I've broken down the course into the following learning modules, each building progressively upon the last. I've provided timestamps in the description to make it easy to jump between sections if you're already familiar with the topic, or if you plan to revisit this video and watch it across multiple sessions. In the first portion of the course, sections 1 through 4, we'll explore why containers exist in the first place, the problems that they solve, and the underlying Linux kernel features that make Docker and containers possible. We'll also install and configure the Docker desktop application and get our first hands-on experience running some containers. For the remainder of the course, we'll be focused on building out and containerizing our own web application, from development all the way through to deploying it to the cloud. This is where the rubber meets the road, and you'll learn exactly how software companies use Docker throughout the application development lifecycle. So what is this demo application we're working with? I'll go into it in much more detail during section 5 and throughout the rest of the course, but in summary, it's a minimal 3-tier web application, meaning it has a front end, in this case built out using React, an API layer. We actually have 2 implementations of this, one in Node.js and one in Golang, to highlight how different languages are handled with containers. And finally, a Postgres database. Each service is designed to be as simple as possible while still showcasing how they all fit together within a real-world application. When we get to the deployment section of the course, we'll learn how to deploy our containerized application to the cloud. Within the course, I'll be using Docker Swarm, which is a container orchestrator built into Docker. And then I've also filmed 2 bonus videos to highlight additional methods of deploying containers, one using Railway and another using Kubernetes. These are separate from the course, and information about where you can find them can be found in the description. This should give you a taste of the variety of options that we have for deploying containerized applications. Before we jump into the course content, I want to pause for a moment to thank the sponsor of this video, Shipyard. Because of their generous support, I can provide this course to you completely free of charge. I'm excited about them as a sponsor because Shipyard is highly relevant to everyone working in the container world. Their platform offers the easiest way to generate on-demand ephemeral environments. In other words, automatically generating fully functional, isolated environments for every pull request. You connect your GitHub repo, add a couple of lines of code to your configuration files, and you can have test environments running in just a few minutes. Later in the course, I'll demonstrate how to use the Shipyard platform with the course sample application. As a bonus for all the students of this course, the team at Shipyard has created an exclusive coupon code for you. The first 300 people to create a Shipyard account and use the promo code DevOps Directive will get 30 extra free days on either the startup or business tier plans. Links and instructions are in the description below. You should go check out the Shipyard platform and consider how it can help your teams deliver better software faster. Without further ado, let's get into the course. Now in this first section of the course, I really want to ground our understanding of why containers exist and why a product like Docker has been so successful. We're going to start with kind of the motivation, and then we'll walk through the history of different virtualization technologies from bare metal to virtual machines to containers, and try to understand how that evolution has occurred and why containers have become the dominant kind of development and deployment mechanism for software applications today. And this meme on the right is one that I've seen shared a number of times. It's this idea that I'm building a software application, I get it running locally, but then something goes wrong in the process of translating that local system to the production one. And so one thing that Docker does really well is help to make it such that our local environment is as close as possible to the production environment that we're going to deploy to. And so that's what this is hinting at, is we're taking that local environment and just shipping it directly to production. Now, there's two main aspects of the software development lifecycle that Docker and containers are trying to address. The first one is on the development side. So up front, as we're building this application, maybe historically, there was this long process. You join a company and they tell you, here's your new laptop, go ahead and install all these things, run these scripts, and get everything configured. And now you can run the application locally and do your development. It was very complex, lots of opportunity for human error. And so then Docker came along, and now setting up your development environment is as easy as running a single command, Docker compose up. We're going to go more into what that is doing later in the course, but it took this whole complex sequence of events that you needed to run and turn that into a singular system and command that everyone can run and be up and running in the first hour of their day. And so making all of the different combinations of Windows and Mac and Linux development environments all compatible is one thing that Docker does really well, and containers in general do really well. And so that's kind of the development side of things. On the deployment side of things, similarly, let's say you would build your application and then you need to put it onto some server somewhere to run it. And there was this idea that there's a number of steps that need to happen. Let's say, okay, we need to create a server running Ubuntu. Then we're going to run some configuration software like Ansible to get all the dependencies configured. And then finally, we're going to copy our application code onto the server and run it with these configuration options. Again, lots of steps, lots of complexity, and much harder to ensure that it's going to be right every single time. What containers do is they bring a single standardized package such that as long as my server has a container runtime, and there's a number of those available, Docker provides one, but there's a number out there, all you need to do is take this standard container image and run it with these specific options, and that's it. So now instead of worrying about the underlying operating system and the underlying dependencies, as long as we have our system and a container runtime and our container image, we can run it and get repeatably reliable results over and over. And so these two aspects are really why containers exist. And you can see how much simpler it gets when we use containers, going from this historical system with lots of steps and potential for error down to a much more simplified, unified approach using a system like container and like Docker. And so that hints at what a container is. I've talked about kind of the standardized package, but from the Docker website, a Docker container image is a lightweight, standalone executable package of software that includes everything needed to run an application. So you can think of it as this box that contains the underlying sort of OS dependencies, let's say runtime dependencies. So if I was writing an app in Python, it would have the Python runtime with the version that is needed. It would have any of the Python libraries that I'm using. So maybe I'm using SQL Alchemy to talk to a database, or Fast API to build out an API. And then it's also going to have my application code. So the specific application code that I'm writing, all of that gets bundled into this container image. And then the beauty is that we have this standard interface and can run multiple copies of it. So let's say I need 2 copies of this application. I can take that image with a container runtime and run a container, run 2 copies, run 3 copies, etc. And so I've used the term container and container image. It's important to know the difference there. A container image is this artifact that has all of these dependencies within it. A container is what you run from that image. So you take an image, and if you think of object-oriented programming, a container image is like the class, and then the container itself that you're actually running is like an instance of that class, an instantiation of that class. And so a container allows us to have this standardized packaging that we can then create one or more copies of, and those copies are going to be the same every single time. So far, I've been using the term Docker container, but I want at this point to call out what is known as the OCI, or the Open Container Initiative. And effectively, there were a few early players, including Docker, building out the early implementations of containers. And as they became more popular, companies realized that rather than having a whole bunch of slightly different but similar things that we're calling containers, it would make much more sense to come together and create one standard that can be used across different implementations. That's exactly what the Open Container Initiative is. A number of companies, including Docker, Google, VMware, Microsoft, Dell, IBM, Oracle, the list goes on, came together and created open industry standards around what a container is and how it should be run. And so there's three primary specifications that the OCI defines: the runtime specification, the image specification, and the distribution specification. So the image specification defines what should be included in the image in terms of metadata and the format that it should contain, so a serializable file system. The runtime specification defines how you would take an image that adheres to that image specification and run it in a container. And then the distribution specification talks about how those images should be distributed. So think about registries and pushing and pulling images. And so these three things together make up the Open Container Initiative. And Docker has a specific implementation of this standard. So when I talk about Docker images or Docker container images, what I'm referring to specifically is the Docker implementation of this OCI specification. If Docker is the only container tool that you're using, it's not all that important to know this. I wanted to provide this context in case you start using other tools and know that there is this standard format that can be shared across different tooling in the ecosystem. Now let's walk back in time a little while and understand how we got to this idea of containers. Hopefully from my description of the motivation, you understand why containers are useful, but I think it's also important to understand the history and the context of how we got to where we are today. And so before there were containers, before there were even virtual machines, we just had computers. We now call this bare metal computing. So if you're running your applications directly on the hardware system itself, another term for that is bare metal. But back long enough ago, this was just called computing, right? So in this case, you have your physical host, your server, the physical hardware layer at the bottom. You've installed whatever operating system you want on top of it. Then you've installed whatever binaries and libraries are necessary to run your application. And then you would have your application, one or more applications, installed directly onto this host machine. Now, what are some challenges with this setup? First of all, you can see that shared layer of binaries and libraries. It's shared across both of those applications. And so if your applications, for example, need different versions of the same dependency or have some dependencies that are somehow incompatible with each other, now we've gotten ourselves into what is known as dependency hell. So we somehow need to either modify our application such that those dependencies are now compatible, or figure out a way to carve up the system such that we can have both versions of the libraries available, doing things like setting your path environment variables differently for the different processes, etc. And so that can be quite a challenge. You also, because of this dependency management challenge, you're more likely to have fewer applications on each host machine. And so it makes it harder and harder to achieve high utilization. So let's say application 1 takes 1 CPU core, application 2 also takes 1 CPU core, but we have this server-based system that has 64 cores. It can be very hard to sort of utilize that compute capacity effectively because of the challenges associated with managing dependencies for applications. You also now, if you are installing multiple applications onto the system, if you ever have an issue with one of those applications or do something that will mess up some underlying dependency, now you have this large blast radius, meaning changes or issues with one application can directly impact the performance of another application running on that same host machine. So it just makes it much more dangerous to modify things. Also, the startup and shutdown speed of a physical system is on the order of minutes. So to spin down that server and reboot it for some reason, that can take a number of minutes. And so it's just relatively slow if you want to try to achieve high uptime and eliminate downtime for your applications. In addition to that, creating new physical machines, sort of provisioning a new system, is very, very slow. So depending on my setup, if I have my own data center and I need to actually order the hardware and get it installed and hook up networking, that could be on the order of days or weeks. If I'm working with a co-location facility or a cloud provider that offers bare metal systems, that provisioning might be on the order of hours, but still quite slow relative to what we'll see as we evolve and sort of add in this concept of virtualization. And so that's bare metal. I think most people are familiar with working with bare metal, even if they don't realize it, because when you run things on your laptop or your desktop, you're installing them directly on the host. And so that is this concept of bare metal. However, that's not the only way to do things. And so these challenges really prompted engineers to come up with this concept of virtualization and adding virtual machines such that we can eliminate some of those challenges. And so in the case of a virtual machine, now this outer boundary is still the host, the physical system, the server. We've got our hardware. We may or may not have an operating system running on that hardware. I'll talk about that more in a second. But then we have what's known as a hypervisor. And so a hypervisor is some combination of software and hardware that allows us to carve up the physical resources. So think CPU cores, memory, access to storage or GPUs, other devices. It allows us to carve up that pool of resources into isolated, smaller pools that we can then install our systems onto. And so this hypervisor kind of gives us this virtual hardware layer upon which we can then install an operating system, install binaries and libraries, and install our applications. And so now, rather than having both applications on the single physical host, we now have application 1 and application 2, each with their own isolated virtual machine running on top of that hypervisor. And so there's two types of hypervisor. Type 1 means there's no underlying OS. These are running directly on the physical hardware. This is beneficial because you don't sacrifice any performance in that sort of OS to software virtualization layer. There's a small performance hit, but much less than if you have an operating system on the hardware and then a hypervisor on top of that. So things like AWS Nitro, so that's the hypervisor that Amazon Web Services is using to create virtual machines on their servers. VMware is a very popular virtualization company, and they have vSphere, which is a type 1 hypervisor. If you want to just create a virtual machine, let's say on your laptop, you're probably going to use a type 2 hypervisor. One such example is VirtualBox. So you can install this program VirtualBox, and then within that, you can create virtual machines for various operating systems, etc. And so how does this compare to those challenges that we saw with the bare metal systems? One, we've eliminated this dependency hell. So now each virtual machine has an isolated set of dependencies, binaries and libraries, such that our application can specify whatever dependencies it needs and not have to worry about the needs of other applications. Because of this, we're going to have better utilization, so we can carve up a big server CPU into many different smaller chunks, and each of those chunks can have its own virtual machine, and then we can install our applications accordingly. So this is what enables a cloud provider. You can go on and see, oh, I can choose between all these different machine types. They don't actually have all those different machine types installed in their data center. They have much larger machine types, and you're getting some sliver of that installed as a virtual machine. We've also reduced the blast radius significantly, such that now if something goes wrong with application 1 on virtual machine 1, that should be isolated from application 2 and virtual machine 2, and it should not cause any issues. And so because of that, we've increased the safety of making changes. We've also sped up the speed at which we can start and stop these things. So now it's still on the order of minutes probably, but faster than shutting down and starting a physical server. And then finally, one area where virtual machines have a big bonus over bare metal is that we can provision and decommission them much, much faster. And so we're all used to living in this cloud world where we can go onto our favorite cloud provider, click the button or issue a command, and have a new virtual server ready within minutes. Or if we're done with it, we can decommission it, and it can also be done, and we can stop paying for it within minutes as well. And so that's the sort of the second tier, or the second rung along this path of virtualization. The next one being containers. And so containers obviously are the focus of this course. They change things a bit further still. So now in this outer box, we've got our host, which could be a physical system. It also could be a virtual machine. So we can take either of those two concepts from before, and we can run containers within that context. You can see at the bottom, we've got either our virtual or physical hardware with an operating system. And then the key piece here that's kind of analogous to that hypervisor is the container runtime. So this is a piece of software that knows how to take a container image and run it within the host system. The key difference between virtual machines and containers is that virtual machines are running their own copy of the Linux kernel. And I'm talking only about Linux containers within this course. There are Windows containers, but that is a different topic for a different day. And so with Linux containers, they are actually they're sharing the kernel with the host operating system. Versus in a virtual machine, you have your own kernel, and you have a copy of your own operating system that's running. And so within a container, you're sharing that with the host. However, we're using certain features that I'll go into later of the Linux kernel to help provide isolation between the different container processes. And so you don't get quite the same level of isolation that you would with a virtual machine. You do get quite good isolation if you configure things properly. As we can see, now we have our two containers both running on the same host. However, they are still isolated and have their own copies of binaries and libraries, even though they're sharing that underlying kernel. Now, there's a couple of different sort of types of software related to containers. The first category of which I'll call the desktop container platforms. So these are sort of container management systems. Things like Docker fall into this category, things like Podman. These are things that you would install on your development system to manage containers, manage container images, run containers, set up the necessary networking, etc. So these are kind of the holistic lifecycle systems. And then there's much more targeted or specific pieces of software called container runtimes, which include things like Containerd or Cryo. And these are very specifically designed to take a container image that adheres to the spec and run it with the necessary configuration options to provide that type of isolated environment that is shown in the image. Now, how does this compare to virtual machines and bare metal in terms of those challenges we saw before? Again, we don't have the issue of dependency conflicts because they each have their own underlying binaries and libraries. We've improved our utilization efficiency even further because we now, for each virtual machine, we had to have an entire copy of that operating system. So each of those virtual machine images is going to be on the order of gigabytes, whereas container images can be much, much smaller because they're able to leverage that underlying OS. And so they're generally going to be on the order of megabytes. I have seen very large multi-gigabyte container images, but that's not ideal. But because of this, we're able to utilize the resources of the system much more effectively. Again, we have a small blast radius where we have some level of isolation, even if it's not quite as strong of an isolation as a virtual machine. We're able to start and stop containers even more quickly than virtual machines, so on the order of seconds. We're able to, in this case, starting and stopping a container is kind of equivalent to provisioning and decommissioning. So also on the order of seconds, we can bring up a new container from scratch and clear it out as well. And then the final sort of key piece, I think, with containers is that they're small and light enough that we now start to use them within our development environment. Sure, you could use something like VirtualBox. You could create a virtual machine that tries to replicate your production environment, but it's kind of slow and clunky, and not that many people do. Some people do, but many people don't. Containers are light enough that now more and more we'll start to actually run containers, and we're going to do this later in the course, run containers within our development environment such that we can have high confidence that our our production environment is as similar as possible to that development environment. And that just decreases the likelihood that we're going to hit some small nuanced bug between the differences there. And so we're able to develop more efficiently using a technology like this. And so I pointed out here that this host can be a virtual or a physical machine. And so now we can get a little bit inception with it, where we have a host machine with virtual machines running on it and then containers running within those virtual machines. And so this is a very common configuration that you'll see most people who are working with containers in the cloud are going to have something like this, where you have multiple virtual machines, each running multiple containers. And so this is just combining all these concepts together. And the real challenge now becomes, how do I manage all of these containers across those virtual machine hosts? And that's where this concept of orchestrators comes in. And so things like Kubernetes, Nomad from HashiCorp, or Docker Swarm are these systems that are designed specifically to take containers and run and manage and schedule them across multiple nodes. And so in this case, the node is each of those virtual machines. And so when we get to the deployment section of this course, we'll talk a little bit more about this. But it's just important to know kind of the concepts of, hey, I'm starting with this bare metal server. My code has to run somewhere on some physical CPU. I'm carving it up into these smaller virtual machines that I'm able to manage a little bit more effectively. But then I also want to gain the benefits and the speed and the efficiency that a container provides. And so combining these different types of virtualization in this way that we see more and more companies using in this day and age. This chart just summarizes most of those challenges and trade-offs that I talked about before in terms of dependency management. Virtual machines and containers really shine. In terms of utilization, containers definitely win out just because it's much easier to get to pack applications more efficiently when running them in containers. From an isolation perspective, you can't get any more isolated than multiple physical hosts. If you're running application A on one server and application B on one other physical server, that's the strongest isolation you can get. Virtual machines still provide very strong isolation, and those hypervisors are these very optimized systems with a small attack surface area that have really been battle tested. And so I think isolation provided by virtual machines is almost as good as those from bare metal. Obviously, there could still be some unknown bug that causes a security issue there, but I think most people have quite high confidence in the isolation that hypervisors provides. And then containers, this is one area where they are less good than these other options, is they do provide some level of isolation. We'll talk about the ways in which they do that, but they don't give the same, they're not as strong. And if you make a configuration mistake, the level of isolation can be dropped significantly. So that's why I gave containers a yellow on isolation. Startup speed, containers win out. The ability to run containers within a development environment, because they're lightweight enough, means that we're much more likely to do so and therefore have stronger parity, or have our development environments and our production environments more similar to one another. This control row is one that I haven't talked about as much. This is just the fact that you can have full configuration control over the system in a bare metal context that you might not get in a virtual machine. So you only have control over the features or the specific configuration options that the hypervisor passes through, or the container runtime passes through. And so maybe there's some specific type of GPU or hardware accelerator that is not yet supported by your particular container runtime or your hypervisor. In those cases, the bare metal system is going to win out, because if you need that specific hardware config, that might be the only way in which you can achieve it. And that leads into kind of this next row of performance. Obviously, a summary of red, yellow, green here can't fully capture the nuances. You don't take that much of a performance hit when you move to a virtual machine or container. However, I think one place that performance can win out on bare metal is because of that control. You're able to do things like, if you're running multiple servers, for example, ensure that they are directly next to each other on the same server rack, such that the networking latency is as small as possible, or ensuring that the storage devices that you're using are directly connected to that physical machine versus accessing them over the network. And so there is performance tuning that bare metal provides the opportunity to do. But overall, the performance is fairly comparable for most use cases across these different technologies. And then the final column there, just sort of how challenging it is to work with. And so if I'm buying and racking my own servers in a facility that's intensely difficult to do and manage, there are now providers that can give me access to bare metal systems and handle some of this operational overhead. But I think it's still more challenging than virtual machines, and more challenging still than containers, where I can spin something up and down very easily. And there's all of these services that have container runtimes such that as long as I provide a compatible container image, I'm able to run it within that system. And we'll see that optionality in a later portion of the course when we get into deploying our own containerized applications. And so now that we have a better understanding of the motivation and history of containers and virtualization technologies, I think it's useful to do a bit of a technology deep dive and start to understand the foundational Linux kernel features that software like Docker is using to make the magic of containers happen and provide those isolated environments that we described. Then towards the end of this section, we'll actually take a look at the Docker system architecture itself. There's 3 technologies that make up the core of a container, and that is namespaces, control groups, and union file systems. And now, namespaces are a mechanism to wrap a global system resource such that from within that namespace, any processes running within the namespace, it appears as though they have their own isolated instance of that resource, and they cannot see things happening outside of their own instance. So for example, on the right here, we have a listing of the various types of namespaces. One very good example is the PID namespace, so the process ID namespace. Within a container, it is isolated with a PID namespace such that the process I'm running appears to be process ID number 1, even though there may be tons of other processes running on the host. From inside the container, we don't know anything about those host processes, and we essentially think that we are the only thing running in this system. Another good one to call out is the user namespace. So by using a user namespace, containers are able to map one user within the container to a different user on the host system. So we could be running as a root user with elevated privileges inside the container, but as long as that container is run within a user namespace that's configured correctly, that root user inside the container may actually map to a non-root user outside the container. And that's very important from a security perspective. In case there was an issue with one of our containers and an attacker was able to gain access to it and break out of that container, if we had properly set up user namespaces, then on the host, they would not have the same level of privileges that they had inside the container. Cgroups are a Linux kernel feature that allow you to organize your processes into groups, which you can then limit and monitor access to certain resources. And so on the bottom left, you can see within the file system under proc/cgroups, we can see all the different cgroups that are available. These correspond to different system resources, whether they're CPU, memory, storage devices, etc. And using cgroups, we can specify a configuration for a particular process or group of processes on how they should be able to access those system resources. And so, for example, we might have one application that is enabled to use up to 30% of the CPU cycles. We would use the CPU.shares cgroup. Maybe it can use up to 50 megabytes of memory. We would specify that with the memory.limit in bytes cgroup. And then we could also limit the amount of disk read that it has access to using the block IO throttle read bits per second device cgroup. Now, the reason that this is important is that it allows us to avoid what's called a noisy neighbor problem, where one application is very resource hungry and sort of starves the other applications of resources. By using cgroups, we can isolate from a performance perspective each of our different processes and each of our different applications. Now, the third key underlying technology is what's called a union mount file system. A specific example of which that Docker uses is called overlay FS. It essentially allows you to take separate file systems and combine them into a unified view that you can then operate on. And so in the image, you can see we have a lower file system and an upper file system with various files. We got file 1, 2a, and 4 in the lower layer. In the upper layer, we have a different file 2b, a new file 3, and then we've actually deleted file 4. When we combine these layers into the overlay, we end up with a combination of those two things, where the upper layer takes precedence over the lower. And so we have file 1, file 2b, and file 3. And so while namespaces and C groups are sort of what make containers possible, it's this concept of a union mount file system that makes containers practical. Because of this layered approach, we're able to share lower layers and cache those layers such that the amount of data that needs to be transferred and stored for container images is much, much smaller, because many images can share a common lower layer, and then only some subset of the upper layers can be modified, which enables us to move less data when we need to get a container image onto a system and allocate less space if we're running multiple copies of the same container. And so with those technologies, while you can interact with them directly, it's software like Docker that takes it and packages it into a really nice user experience. So rather than needing to know all the different commands to create control groups and move processes into them, or create namespaces and block off the different portions of our system in such a way, Docker has bundled that into an easy to use desktop application that we can install in our system and get all of that with a series of simple commands that we're going to learn throughout this course. And so this is a diagram of the Docker desktop application. There's a number of pieces here, so let's call them out in turn. On the left-hand side is the client application, and so this is the thing that we will be interacting with. There's a number of elements. There's the command line interface. So when I go to my command line and type docker run or docker pull, I'm interfacing with that Docker CLI. There's also a graphical user interface which gets installed. This is nice for browsing which images you might have on your system. You can do things like configure how much CPU and memory and disk space the Docker application has access to. So there's a number of nice user experience features that the GUI provides. There's also a credential helper. And so this is when we learn more about registries later on in the course. Essentially, a registry is a place where we can push images to and pull images from. And so in order to have a private registry, you need some way to log in. And so the Docker credential helper is a mechanism to help store the necessary credentials to do the authentication for that. And then finally, extensions are a relatively new feature of Docker that are third-party pieces of software that plug into the client and provide additional functionality in some way. And so that's the client application. When you install Docker Desktop on your system, it also creates a Linux virtual machine. So if I'm on macOS, there's no such thing as a macOS container. Instead, Docker uses a hypervisor, installs a Linux virtual machine, and then within that virtual machine, it sets up two things. It sets up the server host application, and so that's known as the Docker daemon or Docker D. That exposes an application programming interface, the Docker API. And so when I execute a command from the command line, let's say I do Docker run, that command gets passed to the Docker daemon, which is listening via that Docker API. And then it executes whatever the command that is specifying within that server host application. So let's say I did Docker run and then specified I wanted to run my container image 1. It would then go off and create that container 1A. Let's say I then issued that same command, Docker run with my container image number 1 again. I would get another container 1B. And so this Docker daemon is managing those container objects, as well as things like networking and volumes, all within this server host application. Finally, there's an optional Kubernetes cluster that gets configured and installed within that virtual machine. This can be a nice to have if you are developing for Kubernetes. You can leverage that cluster directly without having to install and configure a separate cluster. I mentioned for macOS, it's a Linux virtual machine. On Windows, there's actually two options. You can either configure it to use WSL, Windows System Subsystem for Linux, as the backend, or you can use Hyper-V as that virtualization layer to create a virtual machine. I think either of those are viable. When we go through the installation and setup in the next portion, we can talk through that in a little more detail. And then the final portion to call out on the right, I hinted at this, but a registry is just a place to store your container images and share those container images with your team or with the world or with wherever you're deploying your containers to. And so while it is not a part of Docker Desktop, it's useful to call out here because that Docker daemon, when it needs to get an image that it's not building locally, it's going to go off to some registry. Docker Hub is a great example of one such registry, and pull that image into the host environment so that it can then run the container from it. There's also a little bit of confusion around Docker, Docker Desktop, and Docker Engine. I've highlighted a few of the subcomponents here that make up what's known as Docker Engine. And so that is the command line interface, so that Docker CLI, as well as the Docker daemon and the Docker API. Those make up what is known as Docker Engine, and that is the open source core of Docker. Because the Docker daemon only runs on Linux, you can only install Docker Engine on Linux. You don't get sort of this niceness of the Linux virtual machine and sort of the developer experience that the GUI provides. But if all you need to do is build, run, and interact with containers, then Docker Engine might be sufficient for your needs. In this course, though, because we're using Docker for development, and likely many of you are on Windows and Mac OS systems, we're going to install Docker Desktop so that we can leverage all of the developer experience niceness that Docker Desktop provides. At this point, I think we are ready to go ahead and install Docker on our systems and start using it. One thing that is important to call out is that for personal use, Docker is completely free. You can use Docker Desktop without paying anything. However, if you're using it for commercial purposes and your team has either more than 250 employees or more than $10 million in annual revenue, it does require one of the paid tier subscriptions. So depending on how you're using it within your company, it may or may not be free. So that's just something to call out before we install it. But for personal and learning purposes, it is completely free. Now to install it, we can just go to the Docker docs under docs.docker.com/getdocker. And so in preparation for this video, I actually uninstalled Docker. So I'm going to go ahead and pull open Chrome and go to that site. And so here I am at docs.docker.com/getdocker. It gives us options for Windows, Mac, and Linux. So choose whichever operating system you're on, and then it will have some additional system requirements and information that you're going to need. I'll just click Docker Desktop for Mac with Intel, and it'll start downloading. It is quite a large file, so we'll see. Hopefully my home internet is fast enough. Down below, it has information about system requirements for depending on the type of system that you're running. So you just want to go through and read these. The installation process is pretty much just like any other desktop application. Here it's downloading that .dmg file. I'll then open it, drag it into my applications folder. On Windows, similarly, a pretty straightforward installation process. The one thing to call out is the two different options for the backend. So I described in the architecture diagram how you have your client running directly on your system, but then you're going to have this virtualized environment where the Docker daemon is running. And so this is choosing whether you want that Docker daemon to be running within WSL or using Hyper-V as the backend system. If you are on Windows, I would probably just go with this WSL backend, as that's kind of the default option here. So it looks like my installation file has finished. I'll drag it into applications. It expands from the 600 megabyte download into a 2 gigabyte install. And now I should be able to just go to my applications and click on Docker. It's verifying. It asks whether I want to trust it or not. I'll click open. And so now here is that graphical user interface. One thing that I will call out is you may want to go under settings and then resources. And here you can specify how many of your system resources that Docker as a whole should have access to. So here it's defaulted to 4 CPUs, 10 gigs of memory. I'm going to give it access to a little more memory. The defaults are likely fine for just getting started, but if you find yourself running up against resource constraints, modifying these resource configurations can be very helpful in alleviating those constraints. In order to have those changes take effect, you have to click Apply and Restart. And so I'll do that now. Now, at this point, we can run Docker commands, and installing that application gave us both the CLI as well as the Docker daemon. And so let's run our first container. One fun example that we can use is the whalesay container. And so I can do Docker run Docker/whalesay, and then the command is going to be cowsay, and I'll just say hey team. And so if I run that, it's gonna go off and find that public whale-say image, download it from Docker Hub, so we can see it downloading now. And each of those lines corresponds to one of the layers in that overlay file system. And so it's downloading each of those images onto the host system such that we can then run a container from that image. And we see it took the phrase that I put in here and gave us this nice ASCII art output with that phrase built in. And so with that, we have pulled an image from Docker Hub, run a container from it, and provided a custom command. So that's kind of the most basic thing that we can do with a Docker image. And so that's a fun example, but let's do something a little more useful. Let's say we needed a copy of Postgres 15.1 running for our application. We can just issue a Docker run command, and then I'm doing two options here. One, I'm setting the Postgres password environment variable. That's just something that's needed. The container won't start if you don't set a password. And then I'm also publishing port 5432. And so because these Docker containers are running on an isolated network, the only way that I'm going to be able to connect to it from my host is to publish that port. And so that publish command is saying take port 5432 on my local host, my system, and connect that to port 5432 inside the container. I'm then specifying the Postgres image and specifically version 15.1 running on the Alpine operating system. Again, it didn't have that image locally, so it's going to pull that from Docker Hub. Once it finishes pulling, it then starts up the image, and now we have the database system running inside that container, ready to accept connections. Just to show that it is actually running and accepting connections, we can open up pgadmin. And we can see I've added this Docker database and it was able to successfully connect to it. And we can, for example, run a query. I could do select star from information schema tables and run that. And we get all the tables from that information schema within the database running inside the container. Hopefully this gets you excited about the possibilities of what running inside of these isolated container environments can provide in terms of your development lifecycle. Now that we've run a couple of simple containers on our system, I want to really dive deep on using third-party container images and how we can leverage these within our development process to solve a number of different use cases. Now, Docker Hub is a container registry hosted by the company Docker. There's over 100,000 publicly available images, ranging from things like Alpine and Ubuntu, which are different flavors of Linux, to specific tools such as Nginx, which is a web server and reverse proxy, or BusyBox, which is a utility image that has tons of different useful commands that you can leverage on your system from within Docker. If you go to hub.docker.com, you can then search the images or browse based on the different filters there on the left. And so if there is some utility that you want to use, likely someone has created an image for that. Now, before we go off and create a bunch of containers on our system, I do want to pause and call out the fact that by default, any data that we create or modify within a container at runtime is going to be ephemeral, meaning if that container is stopped and removed from our host, all those data will be gone. Now, there are two mechanisms by which we can help to solve this for dependencies that we want to be in the container when it's started up. We'll want to build those into the image itself, and we'll look at how to do that. As you can see in the diagram on the right, if we remember that overlay, that union file system approach, we have all of our different build layers there, and those at runtime are treated as read-only. So we're starting with an Ubuntu image, we're installing some dependencies, we're copying in our source code, we're running npm install to pull in those node dependencies. All of those layers, when we create a container from that image, are treated as read-only. And then there's just this thin read-write layer on top. That's where any data that's modified at runtime will go. If there's some additional dependency or configuration change that is needed, rather than starting the container and then making that change, where that change would live in the read-write layer at the top, we'll want to pull that into our build process such that every time we create a container from that image, it will have the necessary change. Now, the other case with data that we may want to persist are data generated by the application at runtime. So this could be things like data that we're storing in a database when a user creates or modifies some aspect of their profile, let's say on a website. Those data we can't incorporate into the image because they're not known at build time, but instead we need to store them in such a way that they will persist beyond the lifecycle of the container itself. Now, there's two mechanisms to do that. The first of which is called a volume. And so we can create what's known as a Docker volume that will designate a particular location within the Docker host system. So it will be within that virtual machine that Docker is running, located at /var/lib/docker/volumes. We can then, when we run a container, tell Docker to use that volume and mount it at a specific path within our container file system, such that any data we store there gets stored in the volume, and that can be managed separately from the lifecycle of the container itself. Now, the second option is a bind mount. And so where the volume mount, the data is still stored within that virtual machine on the Linux file system. With a bind mount, we're actually connecting our host file system into the container at runtime. So I'm going to have some path on my system, and then I'm going to mount that into the container at runtime. And now if I modify any files within that path, they'll show up on the host file system. Both of these are viable options. Docker suggests using volume mounts by default. One reason for this is that because that bind mount is crossing the boundary between our virtual machine and our host system, performance can be much lower if we are doing things that have a lot of reads and writes. And so by default, use a volume mount. If you need to have easy observability into the data that's being modified, or you want to be able to see the files that are being created more easily, then a bind mount can be a good option. Also, later in the course, we'll use a bind mount to actually mount our source code into the container such that when we make changes and are developing on the fly, those changes can be represented within the container file system right away. I just covered a lot within this one slide, but I created a walkthrough in the GitHub repo that we'll do now that I think will really solidify these concepts. So the README for the fourth module of the course, so the running third-party containers module, has all of this within it. And so now I'm going to walk through the process here that is outlined in this README. And I think it will make what I was just describing much more clear about data persistence. So remember, our container file system looks like this. We have a number of read-only layers that exist in the image. And then we have a read-write layer at the very top. Let's do some experimentation with running a container, installing something in it, and seeing how that behaves when we create additional containers from that same image. So let's start by doing a docker run command, and we'll pass it the --interactive flag and the --tty flag. Those two flags together mean that when we issue this command, we'll get a running shell within that container. The --rm flag tells Docker that once this container process exits, so once we exit the container, it should not store that stopped container. It should actually remove that from our system. So if we run this, it's going to go off and pull that Ubuntu 22.04 image. Then it starts the container. And now we're running a shell inside that container. Let's try to ping google.com from within the container. As you can see, the ping command is not found. It's not installed by default within that Ubuntu image. To install it, we can use the apt package manager. We can do apt update. That'll go off and fetch all the metadata associated with the apt package manager. And then we can do apt install iputils ping. I'll say yes. And so now with ping installed, we should be able to call ping google.com one time. That's the -c1. It successfully pinged Google, and that's great. Now I'm going to exit this container. And if we want to take a look at the container ID here, dd61, we'll get a different container ID the next time we create one. So now I'm going to rerun that same command. We're going to create a new container from that same image. And you see we have a different container ID. This container doesn't know anything about that previous one. And so because we installed that ping command within the read-write container image of the other container, it was blown away completely when we exited and Docker removed that container. So now that we're in this container again, if we try to do ping, ping is not found. However, let's change this experiment just a little bit. So I'll exit this container, and now I'm going to run the same command, but I'm going to remove this --rm flag. So Docker's not going to throw away the container after it stops. And then I'm going to add a name option. And so I'll name it my Ubuntu container. And now we have a shell inside that container. Again, we're going to do apt update and apt install, and that will get our ping utility installed within the container. Okay, so now with ping installed, we should be able to use it. Great. And so now when I exit, because I didn't have that ---- remove flag, the container still exists on my system. If I do a docker ps, that will list containers, but because it stopped, it doesn't show by default. So I'll do a -a, and we can see my Ubuntu container was running. It was created 41 seconds ago. It exited 13 seconds ago, but it should, this container, even though it's in its stop state, still has that read-write layer associated with it. So I can now restart my container with the docker start command. So I'll do docker start and pass it my container name. And then I can use the docker attach command to attach to the shell running inside that container. So now I'm back inside the container and I can ping Google and it works successfully. So that just shows we created a container, we installed the dependency in that container layer, we stopped the container but did not delete it, and then we were able to jump back in that same container and that dependency existed again. Now, normally we would never want to jump into a container and modify things like this on the fly. The better approach, and the approach that we'll want to use for a dependency like this, is we want this to always be there when we start a container from that particular image. So instead of starting the container and persisting it in the container itself, instead we want to build our own image containing that dependency. And so we're going to do a much deeper dive on building containers and optimizing those builds in module 6, but we can write a very simple Docker file here and pass it at the command line. So this is just saying start from that Ubuntu container image, run the apt update, apt install, and that passes it to the Docker build command. And then we're going to tag it with this tag my Ubuntu image. So if I run this command, Docker is going to build a brand new image based on the original, but now this new image is going to have IP utils installed out of the box. If I want to run a container based on the new image, I'll use the tag specified in the build command. And now I don't have to install ping because it's already installed. So now I can run ping Google and it succeeds. So hopefully that gives you a better idea of how this container file system works, and the fact that if we want some data, likely in the form of a dependency or configuration, to be available at runtime every time, we want to build that into the image. We don't want to start an image and then make modifications to get it to the state we want. And so that's the case of data that we know about at build time and can build into the image directly. The second use case that I described was data produced by the application at runtime. And so, like I mentioned, this could be data that's going into a database. Let's do some experimentation to build up some intuition about this type of data. Again, I'm going to create a container from that Ubuntu image. Now this time I've shortened the --interactive --tty. You get the same thing in a shorthand version with just -it. And so here we have a shell running in that container. To simulate data created at runtime, I'm going to make a directory called my data, and then I'm going to echo hello from the container into a file within that directory. And so now if I cat my data hello text, we can see hello from the container stored in a file on the container file system. If I exit the container, run a new container from the same image, what do we expect? If I try to do cat my data hello text, of course, that file doesn't exist. Just like when we installed something into the file system, it's in that top read-write layer that gets blown away with the container. But now we can no longer build this into the image because we don't know what this file should say ahead of time. So instead, we're going to use a volume. I can run docker volume create my volume, and that creates a volume. And now I can modify my run command such that I mount the volume into the file system of that container. So I've added this --mount flag, It's using the source of my volume, which I just created, and it's using a destination of my data, root/my data. Now, I'm going to do exactly what I did before. I'll do make dir my data. Oh, it already exists because I mounted that volume. That directory was already created. So I'll echo, just like before, hello from container into a file within that directory. I'll cat it. Our data exists within that file system. But if I exit and then recreate a new container, also mounting that same volume, we can go into my data and see that hello text has persisted across that container destruction. So the data was stored in the volume. Even though we stopped the container and Docker removed it from the system, the volume is treated separately. And so we were able to persist the data across that container boundary. Now, you might be wondering, where does this file actually live? It has to live somewhere on disk. And in this case, because I'm on Mac OS, it lives within that virtual machine that Docker is managing. So if I was on Linux, it would just be directly at var lib docker volumes. Because I'm in Mac OS, I don't have var lib docker volumes. That lives within the virtual machine. One way that we can take a look at that is to run this privileged container. So this is a nifty trick that I saw online where I can run this command and it will essentially give me a shell into that virtual machine that Docker is running. And now I can navigate to var lib docker volumes. I see a whole bunch of volumes. The one I care about is the one that I named my volume. Now if I go into the data directory, and I see my hello.txt. And so this is showing in that virtual machine file system where that volume actually lives. Now this was just a trivial example where I was creating that file and wanted it to persist. Let's say we were running a database, like we were running Postgres before, we would want to use the same approach with a volume and mount it into the file system of the container where Postgres was going to store its data. And so by default, Postgres stores at /var lib Postgres data. And so we would want to modify our command to use that mounting syntax. There's an alternative syntax with the -v that does the same thing. And this would allow us to store the database data in a volume and manage that separately from the container. Now, I mentioned that volume mounts were one option and bind mounts were the other. Let's explore what a bind mount looks like for the same use case. Now, I'm going to take my command that I used before, where I had a volume mount, and change the type to bind. So now the type is bind. My source is my present working directory, and in particular, the my data directory within my present working directory. And so let's just list out to show I have a my data directory here. Within there, there's already a hello.txt. Let's remove that. So now there's nothing in my data. And if I run this command, I'm going to mount that directory from my host file system at the present work directory /my data, and the destination is going to be root/my data on the container. So let's echo something in here, blah, blah. That's going to go into hello.txt. So inside the container, we have blah, blah within hello.txt. If I exit that container, I'm now on my host system. And if I cat my data hello.txt, we can see that file was created and stored at the path that I specified. I can also modify the host data, and that will be reflected inside of a container mounted in the same fashion. So I can do, I'll add another blah. Okay, so it's 3 blahs outside the container. I'll now recreate my container. It'll actually be a new container, but still mounted at that same path. And if I do cat my data hello.txt, we see the updated version reflected inside that container. And so as you can see, bind mounts, just like volumes, are a mechanism to persist data beyond the container lifecycle. The volume mount is kind of tucked away inside the file system that Docker is managing. The bind mount is located on my local system. By default, Docker suggests using volumes. They're slightly easier to manage. However, if you want easier visibility into the data itself, it can be convenient to use a bind mount. Just be aware that you can suffer some performance impacts if you're doing heavy read writes into the bind mount location. So my hope is that this has helped to build your intuition around how data is handled within containers, both sort of the default case, then the case where we want dependencies available in the container when it's started, and then the third case where data is generated at runtime, and sort of how we should manage each of those, either by building those data into the image or by mounting a volume or a bind mount to capture those data beyond the lifecycle of the container. The other thing that I've called out within this README that I think you'll find useful are specific use cases for leveraging third-party containers directly. And by that, I mean not needing to build our own container image. The first one is databases. So databases are always a pain to deal with. Sometimes you need one version, sometimes you need another. Sometimes you'll have multiple databases that you'll want to interact with for different projects. Docker provides a super useful mechanism for spinning up a new container with a different database that you can use and have that completely separate from one application to another, from one version to another, very, very easily. I think the key considerations are to always use a volume to persist the data. If you have additional configuration that you need, so let's say there's a config file that you need to have in the container when it's starting up in order to set some specific configuration, you can use a bind mount to mount that from your host file system into the container. And then finally, you'll want to set the necessary environment variables. So a number of the official database images use environment variables to configure things like the root password within the container. So earlier when we started that Postgres container, we had to set the Postgres password environment variable. There's a number of things like that with these database container images. I've laid out a number of different databases, and I've tried to capture the specific volume mounts and environment variables that you might need to use. So we've seen Postgres before. Here I've added that volume mount for the location where the data gets stored. If you had a custom PostgreSQL conf file and didn't want to use the defaults, you would modify this command to use this bind mount. So you would have this on your local file system, and then you would pass the -c flag to the container when you run it, and pass it a path to that flag. So this is, as you can see, where we mounted inside the container. This is that same path, and that tells the container upon startup to look there for the configuration file. So MongoDB, the official image, it looks quite similar. As you can see, it's expecting to save the data to /data/db, so we're putting that into a volume. We're setting the initial root username and password with environment variables, and we're publishing the default port of 27017. Again, if we have a specific configuration file we need to pass in, we're going to bind mount that into the container, and then we're going to pass a configuration flag to tell Mongo where to look for that. I'll let you look at the rest of these on your own time, but I've laid out the commands for Redis, MySQL, Elasticsearch, and Neo4j. Now, the second use case that I think using third-party containers is super useful for is when you need an interactive test environment for something other than what you're running on your laptop. So I'm running macOS, but sometimes I need to test out commands in Ubuntu or Debian or Alpine. And so being able to run this quick command and have an interactive shell within that specific Linux flavor is really priceless. Like, I can test out commands and iterate on them so much more quickly if I'm writing a script that's eventually going to be run in that environment. I'll just create a container using one of these commands, and then I have an interactive environment where I can test things, figure out the exact syntax, use the help commands, etc. Interactive test environments for operating systems or for programming runtimes, we can do something very similar, but instead of having a shell in the OS, we'll have a REPL in our command line with a particular version of that programming runtime. And so if we're testing something that needs Python 3.11.1 versus 3.11.0 or some minor tweak, It's so easy using Docker to get an environment that has the exact versions that we care about for doing that type of test. Now, the final sort of use case that I find super helpful for using third-party containers are command line utilities. Sometimes you just won't have it installed or you don't have the right version. And so people have bundled up these utilities. And because so many Unix tools are designed to pass data as text from one to another, so we can pipe data from one command to the next, we can pass data into these containers and get the output as a stream. We can use these without actually having them installed on our system. So JQ is a utility for working with JSON data. And so, for example, if I run this command, so if I jump back here and we look at the sample data I have here, so let's say I have this test.json, it has key 1, value 1, key 2, value 2. If I run this command, it's going to take that test.json data file, pass it into this JQ image, and perform this command. So it's going to find the value located at key 1 and combine it with the value located at key 2. And so in this case, I get value 1, value 2 as a string, and that's the output. And so without having JQ installed on my system, I'm still able to use that utility directly with Docker. YQ is similar to JQ, but is for YAML. There's also command line interfaces from cloud providers, such as the AWS command line or the Google Cloud Platform command line, and you can run those in container images. You will need to mount in your credentials. So by default, we know that the container is not going to have access to the host file system. And so if your credentials are stored at, let's say, the .aws directory within your home directory or the .config directory within your home directory, you'll need to craft the correct volume, the correct bind mount commands to get those credentials into the CLI. But once you do that, it allows you to use different versions of the CLI very easily. And so if there was a breaking change from one version to the next, you can leverage that previous version without having to reinstall and modify things if you've already upgraded. Now, this sounds cool, but you might be thinking, I don't want to have to type out Docker run, blah, 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 with all these bind mounts, etc. And so one way that we can improve the ergonomics of this quite a bit is to use two concepts. One is a shell function. So we can write a function like this that will take this command and essentially invoke it when we run this function. We also can use an alias to do the same thing. To close out this section, I wanted to pull up a talk that was given by Jesse Frizzell. I think this was in 2015. So this is quite a few years ago. Docker was much younger in its maturity. However, she was an early adopter and an employee at Docker and used to run all sorts of things within Docker. And so I think this is a talk that is worth watching for sure and just sort of shows that you can pretty much run anything in containers. Giving it a watch is really interesting and inspiring and helps to understand sort of this mindset of, I don't necessarily need to install everything on my host system. She goes a little further than most with this concept, but I think it's still eye-opening to see the number and types of things that she's able to run in containers. So with that, we've reached the end of the first portion of the course in which we learned the history and motivation of Docker, about the underlying technologies. We installed and configured Docker such that we're now able to run containers and interact with them. And then we saw some use cases for leveraging third-party container images for different things throughout our development lifecycle. At this point, we're going to shift gears and start building our own containerized applications. I think it's important to realize that learning Docker in a vacuum doesn't actually provide much value. And so instead, we want to have some realistic web application with which we can apply this technology. In this module, I'm going to walk through a sample application that I've built for exactly that purpose. It's a minimal 3-tier web application. And by 3 tiers, we have the front end or the client that's built in React. We have an API layer, application programming interface layer. We have one API built in Node.js, so that's an interpreted language, one built in Golang, a compiled language. We have both of those. They're almost identical, but I wanted to show 2 different languages with 2 different developer toolchains so that we can showcase how Docker handles those slightly differently. And then we're going to have a Postgres database. I've tried to keep each of these components as simple as possible while still being representative of the type of application that you might see in a modern web technology company today. The implementation of each of them will be quite minimal, but how we configure things like networking and passing credentials will be realistic to an application at a web technology company. At this point, I'll jump over to my code editor and walk through this code at a very high level. I'll point out though, because this course is focused on Docker and containers and not on web application programming, I'll keep this relatively high level just to give you an idea of the things that the code is actually doing and highlighting the configuration surface area where Docker is going to interface with them. At this point, if you haven't already, you'll want to go to the companion repo for this course. I'll have a link for it down in the description, and you can find all the source code that we'll be going through and building out. And what you'll want to do is here under code, you can either click here and clone it to your system, but even better is if you fork it, because that way you can make modifications, commit those modifications. And if you have any improvements you'd like to make and propose back to the course for others to use, you could create a pull request back to my copy of this repo on GitHub, and that would be awesome. While you're here, if you don't mind giving it a star, that would be super helpful to help the project grow. And while I'm asking for your support, you may as well hit the thumbs up button on the video as well. And so with that, let's jump over to the text editor and see this demo application. So I've got the code editor up here, and we're in module 5, the example web application. I'm going to start by running the database. Just like we did in module 4, I'm going to run the database with a Docker run command. I'm going to pass it a Postgres password environment variable. I'm going to use a volume mount, like we talked about, to persist the data outside of the container in this volume so it can live beyond the lifecycle of this particular container. And then I'm going to publish port 5432, which is the default port that Postgres runs on. And I'm using Postgres 15.1, and in particular, the Alpine variant. So this is a makefile. Each of these is called a make target. We can do make, run, Postgres. And now we have that database running in a container. I can do the Docker ps command to list out the containers running, and we can see here's the container. This is the image it was based on. Because I didn't specify a name, it generates a random one. And we're publishing that port so that I can connect from my local host. At this point, let's move and take a look at the Node API and get that running as well. So it's located within this API node subdirectory. If we look in the package.json file, we can see there are just a couple of dependencies. We have Express, which is a package for building REST-based APIs. We have Morgan, which helps us configure logging for that API a little more easily. And then we have the PG package, or the Postgres package, which is going to allow us to create a client and connect to the database. So what I'm going to do here is make sure I'm running the right version of Node. So I have NVM installed, so I can do NVM ls. It'll list out the different options that I have installed on my system. I want 19.4, so I'll use NVM use node 19.4, and then I'll do npm install. It's going to grab those dependencies from the package.json and install them in my system in this node modules folder. If I wanted to run the application, I would do npm run dev, but I also need to pass it one environment variable, and that environment variable is the database URL. So this is going to give the application the information it needs to connect to that Postgres database running in the container. And so again, I have this command laid out here, and so I'm just going to do make run API node. And now it's started up and listening on port 3000. Let's just go see how that application behaves. If I load it up, we see at the root path, so I haven't specified any path, it returns the current timestamp, and I'll show you how this is working behind the scenes, but it's just querying the database, asking for the current time, and then returning that. And then I have the API node key and value just to show this is the node-based API. We'll have an almost identical response from the Golang API, except this will say Golang instead of node. For each time we refresh the page, we're seeing there's a 200 response. That's a successful HTTP response for the request. And then we have this 404 for the favicon. So because I'm loading it from a browser, it's also trying to load that little icon that you would see in the top left corner but it doesn't have one. So that's the 404 not found error that we're seeing there. Now let me just look very briefly at the source code for this application to show you what it's doing. We've got two primary files. Index.js is the main one. We're importing some dependencies here at the top. We're setting the port number that we're listening on, defaulting to port 3000. We're setting up some logging. And then here's where we define that API endpoint, where we call our getDateTime function, which I'll show you here in a minute. And then we populate the we populate the API key within that JSON object as well. In our database, our db.js file is where we have that function. It's where we're gonna load in our connection, our credentials, so that we can connect to the database, instantiate a new pool, which will be that database client, and then make the necessary call to the database to get the time that then we can return on that endpoint. And so that's pretty much all there is to this Node application. Like I said, I wanted to keep this as simple as possible while still highlighting the types of networking and configurations that we would need in a real-world application. At this point, with the Node application running, we can move on to the Golang application. And so for this one, it's located at the subdirectory API Golang. Here I am within that directory. To install the dependencies, I would do go mod download. First, I'm going to set the go path just to tell it where to download those modules to set a workspace. I've got this go workspace subdirectory. I can export go path, and that will point to that subdirectory. Now if I do go mod download, it's going to look for the dependencies that are in my go mod file. And so the two dependencies that I've added here are Gin, which is an API framework, and PGX, which is a Postgres client. And so that go mod download looked in go mod, brought those into my workspace. Okay, so now we should have all of our necessary dependencies. And just for reference, I'm using Go 1.19. And so to execute this program, I would do go run and then point it to the main.go file. That's going to both build the application and run that built binary. Again, just like the Node application, I either need to pass it an environment variable with the database URL or pass it a file containing those credentials. I have a command in my make file that does just that. So I can do make run API Golang. We see it passes that database URL in as an environment variable and then executes our Golang and then does go run main.go. That's running on port 8080. So I can go here and reload this. And very similar response to the Node.js one. We have API Golang, and then it's grabbing that timestamp from the database. Each time I refresh, it gets an updated time. And so just very briefly, I can take a look and show you the implementation here. I'll pull open the main.go file. As you can see, we import our dependencies here at the top. We then have our init function. Within there, we're loading in the credentials that we need to connect to the database. Once we do that, we pass those credentials to this initDB function, which is defined in the database module that I'll pull up here in a minute. And then within our main function, we have our endpoint defined where we call our database.getTime function and take the results of that, and we return that JSON object using Gin. I'll just pop open the database module here just to show you the two functions there. We've got our initDB function where we're taking our connection string with those credentials and initiating a client. And then I have this getTime function, which just like in the Node implementation is calling select now as now, getting those data back and returning that to the caller. And so that's really all there is to this application. Like I said, almost identical to Node. We just want to have both of these different languages so we can show how to manage the different tool chains, how we're going to build the Docker container images, and how we're going to create containers from those images. Now with the Golang API running, The final piece of the puzzle is going to be the React client. So that implementation is here in the client React subdirectory. Once again, we can look at the package.json. We have a handful of dependencies. We have React and React DOM. Those are installed by Vite when I created this project. I used Vite to do so. And then I added Axios as well as this React query package, which just enabled me to very easily call my APIs, get those data, and feed that data into my React components. So I'll want to, once again, just make sure I'm using the right version of Node. I want 19.4. Great. I'll do an npm, make sure I'm in the right directory. Then I'll do npm install. This goes off and downloads all those dependencies, brings them into my local node modules folder. And then to run it, I'll just do npm run dev. And by default, Vite is going to run that development server on port 5173. So if I load the page here, we see the result. It's a React app. It calls both of those APIs, gets the data and returns them. Each time I refresh, you can see that the timestamps are updating. And so that's doing exactly what we want it to do. Once again, I can give you a quick look at the source code just so I can show you what it's doing. All the logic pretty much is in this app.jsx file. We're pulling in our dependencies at the top. I have this function-based component called current time that uses the useQuery method and Axios to make a get call to the API that's specified. And so this enables me to use the same component for both of those APIs by passing the API in as a prop. I then get the data back and can use that within my component. And then down here, this is the actual content that's going to be displayed. I just have which API it's coming from data.api, and then the timestamp that was returned in data.now. While it's still fetching, it will have this placeholder updating text. Here at the bottom is the content of our app itself. We wrap it in this query client provider. That just enables us to use the functionality within that React query package. We've got our static header, and then two instances of the current time component. One where we're passing it the Golang path, one where we're passing it the node path. It is important to call out here that within my vite.config, I have these proxies set up such that API Golang is sent to localhost 8080, where the Golang application is running, and then API node is passed to localhost 3000, where the node API is running. That's pretty much it for this configuration. Hopefully that didn't seem too overwhelming. It's quite complex trying to run all of these services independently and get them all talking to each other. That's kind of the whole point of this course, right? I want to avoid having to set up each of these services separately and avoid the complexity of needing to match the right version on your system versus my system and Mac versus Linux versus Windows. Docker is going to help us simplify this dramatically. And so as we progress through the rest of the course, we're going to take these components, containerize them, and then learn how to run those containers, how to configure them properly, and how to set up a development environment such that we can very easily go from zero to rapidly developing and iterating on our applications, all within a containerized setup. And what I really tried to do with this application is have each component be the absolute minimum complexity while still giving us that application, the networking, the configuration be representative of what you would see in a modern day web technology company. And so ideally, don't get bogged down with any of the particular applications themselves, but just try to understand, here is the core of what it's doing. We have our client on the front end. It's calling those two APIs, so we need the networking to be set up properly there. Those two APIs, instantiating clients and connecting to that database and making a database call. So we need to handle those credentials properly, as well as the networking between them. And just generally, we need to have our environment set up for each of these applications to run as desired. Now that we have our example application, we can go through the process of containerizing it. Now what that means is that we're going to create a specification, and then we're going to build from that specification our container image. The specification is what is known as a Docker file. So it's a text document that's going to have all the commands that we need to create and assemble this image. You can think of it almost like a recipe for your application. You're going to start with some base layer like an operating system. You install your language runtime and any dependencies and tooling associated with it. Then you would install your application dependencies. You might set up your execution environment with certain environment variables. And then finally, at the very end, you're going to run some command that starts your application. Now, this Docker file is paired with what is called a build context. So we write all of our instructions in the Docker file, and then the build context is generally a folder or a directory on your local system containing all of your source code. It can also be a URL, so you can pass like a public GitHub repo as a build context. And we take these two things together and run the Docker build command. And with those information, Docker is able to go off, follow the instructions in the Docker file, and produce a container image. I'll call out one additional file that's important to know about, and that's a Docker ignore file. Within your build context, you can include this .docker ignore file. As the name suggests, you can tell Docker to ignore certain files. So let's say we've installed the node modules locally. We definitely don't want to copy those into the container image because we're going to install them within the Docker file. And we could have incompatibilities from the installation on our host system to that within the container. And so with this as sort of the high-level framework, let's go ahead and start writing some Docker files for our example application. As we go about writing our Docker files, this page within the Docker documentation under docs.docker.com engine reference builder lays out all of the valid commands that you can use within a Docker file. The format is actually relatively simple. If we use a hash, that's a comment. There's a convention of using all caps for the instruction, and then we'll pass arguments after that instruction. So for example, we can have a comment saying what this step is doing. Then we can use the run command, which is going to run this during the build phase and then echo something out. If we scroll down here on the right, you can see all the different options that you can pass with the run command, as well as all the other commands that are valid. We're going to use a number of these, and I'll try to call out all the ones that you're going to need to know along the way. So let me just jump into the code editor, and I will create a Docker file in my API node subdirectory. And you might notice that I have the 05 module as well as the 06 module. I have a whole bunch of Docker files here that show kind of the sequence of events that we're going to go through. But just for purposes of demonstrating building it out, I'm going to put it in the 05 directory. And generally, you would want to do this. You would want to put your Docker file in the place where your code is living. Let's think about what that recipe might be for my Node.js-based application. I need to start with some Linux distribution. And so let's just use Ubuntu. So I'll use the from instruction, and then I'll specify an image name. So Ubuntu. We also then are going to need to install the Node.js runtime, and I can use the apt package manager to do that. So I'll use the run instruction, which is going to run this command during the build phase. I'll do apt update. That'll grab all the latest metadata from the package manager so that I can find the correct package. And then I'll do run apt install node.js. And let's just execute the build now just to make sure these steps are working properly. I'll navigate to API node. And then to build this, I can just do docker build with a period. I didn't specify a name of a Docker file because the default is to use Docker file with no extension. I pass my current directory of period as my context. So it looks like it failed because that apt install command is interactive. And so I need to pass it a dash y, and that'll override that question and automatically install. So let's try building it again. Now it looks like it's installing Node.js. And you can see each of our steps, we started one of three, we pulled that Ubuntu public image, then step 2 of 3, we ran that run apt update, and then in 3 of 3, we installed Node.js. And so if we think back to that union-based file system, each command in this Docker file is adding a new layer to that system. And so oftentimes we want to minimize the number of layers and think about, because Docker is caching those behind the scenes, how we can avoid invalidating the cache. One such method that we can do to improve this already would be to run these on the same line. So rather than doing the apt update and then the apt install, we can combine them into a single command here. And so now those two actions will get combined on that single layer. Okay, great. So now how are we going to get our application code into this container image? And for that, we're going to use the copy command. So this allows us to copy either from our host system or later we'll see how to copy from another container image during the build. And so I'll copy, and I'm just going to copy my entire current directory into the image. We're going to improve upon this later, but this is just a simple way to do it for now. And so with that, we'll have our source code within the container. Then I can run the npm install, and that will go off and grab all of my dependencies. So let's just make sure this still builds. Okay, so npm was not installed. So we also need to install npm. Okay, and now that we had npm installed in the system, we're able to execute our npm install command. And then the final step that we need to do for this Docker file is to add a command that will be executed at runtime when we create a container. The format for this is we'll have an array of strings. And so in this case, I'll do npm run dev. And that would run my dev script from the package.json file when we start it up. So I'll build it once more. And one thing to note here is that I changed something in my Docker context, and now when I'm rebuilding it, it's executing run npm install. And that's because this copy step came before the npm install, and so making that modification actually invalidated the cache. And so it was much slower to build because we had to run npm install and download all those dependencies. We'll address that in a future improvement. Now, in order to be able to execute this Docker build command builds it, but doesn't actually tag it with any name. And so I could run this, I could reference it with this SHA directly, or I can add a -t, and I'll call this API node and call it version 0. Now I can do Docker image list, and we can see API node version 0 was built a minute ago. And look, it's almost a gigabyte in size. Now this Docker file, while functional, is terrible. There are so many ways upon which we can improve it. And now let's go through and think about what those are. First of all, starting from Ubuntu and then installing Node and NPM, while we can do that, there are a bunch of official images on Docker Hub for language runtimes. So if I go to Docker Hub and search Node, it'll pull up the official image. And so this is a Docker official image. It has that tag. It's been downloaded over 1 billion times and has over 10,000 stars. And they maintain all of these different tags for different variants. And so if I do this, I can remove this install command and instead go straight from Node. And so let me build that again as version 1. And so for any runtime, any language runtime, there's probably an official image that will maintain all the different versions you need and have things pre-configured out of the box. So usually you can start from Node or from Python or from Golang. And we'll see that when we go to the Golang API as well. Now you'll also notice that I don't have a tag specified here. I have the image name, but no tag. And what that'll do behind the scenes is it just assumes that I mean node latest. That's a problem because that node latest tag can change based on the images that the maintainers of that image have pushed most recently. And so rather than tag it with latest, it's much better practice to specify an exact version. And so what I'm going to do is look here at the versions. Alpine is a Linux distribution. It's quite small and therefore good for building Docker images, because as we're thinking about final image size, that base image that we're building from, that's as small as we can get. And so it's really important to choose a small base image. It's also good from a security perspective to have fewer utilities and dependencies installed from the get-go. And so instead of using node with no tag or node latest, I'm going to use node 19.6.alpine. And so I'll build that once again. And I'll call that one API node 2. And just to show you what a huge difference that makes in terms of image size, we can do docker image list and scroll up here. And we see node 0 was the Ubuntu based one. This tag number 1 was the just node latest version. So that's over a gigabyte. And by using that Alpine base image, we've cut our image size by a factor of 5 and we're down to 200 megabytes. However, you will notice that each time I'm building, it's taking quite a while. And the reason for that is I'm copying in my entire source directory before I do the npm install. So I keep invalidating the cache. And so the way that we can get around that is that rather than copy the entire source directory right away, we can first copy in only the package.json and package lock.json files, and then do npm install. And after that, copy the remainder of our source code. By doing it this way, this layer will only be invalidated if we change our dependencies. And so I'll call that tag number 3. It's also best practice to specify what's known as a working directory within the image. That's the default directory in the file system where commands in the build process are going to be run, or the command at the end that we're running is going to be executed when we instantiate the container. We do that using the workdir instruction. And this is going to depend on the convention of your language or framework that you're using. In this case, for Node apps, I like to use user source app. That's not really going to change anything about our system, except that now within the image, instead of copying all of our code to the root directory and installing the node modules there, it's going to copy things to this path, which just keeps things a bit more organized. Also, I have things within my API node directory that I don't want to be copied into this image. There's 2 things that I can do to help avoid that. One, I can add this docker ignore file. And in this case, I'm specifying the node modules directory. So I don't want the node modules that I've installed on my Mac OS system to be copied in, because that would cause conflicts. And so by putting it in this docker ignore file, those will not get copied in. I also can specify, let's say I only want to copy in my source code directory. I don't need to copy in the remainder of this stuff into the image. And so I can do that here. I'm only copying the source code directory into the container image. Let's build it once more. We'll call this 4. Now, because this is eventually going to be a production container image, I don't want to be running npm run dev here. Instead, I want to run node and then point it to my index.js file. And so rather than execute this npm script, I will just say node and then index.js. And so that index.js file on my host system is in the source subdirectory, but because I'm copying from source to my working directory, it will be in that working directory, and I can just call it that way. So I'll call that one 5. And now most of the improvements that we've been making so far either have to do with image size, build speed, etc. Another key aspect that we can influence by changing and improving our Docker file is the security of our container. And so one very useful technique is to execute as a non-root user. And so this Node.js official image happens to have a user defined in it called node. And so by using the user argument and passing it the name node, it will use that user. Now that I've done that though, I want to make sure that the files I'm copying in here are owned by that node user. So I can use the chown command, node, and now all those source files being copied in will be owned by that user and be accessible by that user. So I will copy this, tag this as number 6. Now, many Node.js applications look for an environment variable called node-env. And so we can use the env argument or instruction and set node-env, and we'll set that equal to production. If it's set to production, the application or the package will behave one way. If it is unset or set to anything other than production, it will run in a development mode, and we don't want that for a production image. So by specifying this environment variable here, that can be very useful. I'm also going to change from an npm install command to an npm ci command, and I'm going to add the only equals production option. And so these two things together, the npm clean install is what CI stands for. will look for the specific versions from my package.lock file and install exactly those versions. So it gives a much more repeatable build. And the -- only production option says don't install my dev dependencies. So I have things like jest and nodemon in my dev dependencies within the package.json. Since I don't want those or need those in my final production image, I can use this -- only flag to achieve that. So let me call this number 7. And now I know, as the person who wrote this app, that it is expecting to run either on an environment variable named port that it loads, or it will default to port 3000. I'll add a command called expose and just say 3000. And so this doesn't actually change anything about how the container image behaves or the container. This is just documentation for users of this image that it is expecting to run on port 3000. That way they know to publish that port to the host or to whatever system they need to, so that they can get traffic to the app. And now there's one additional place where I can make improvements, and that's in this step. And this again is going to be to improve our build speeds. There's the option to mount a cache location to store information from this step specifically. So I'm adding this mount type cache with a target of this location. And then I'm telling NPM to use that location to store its cache dependencies before calling my NPM CI call. And what that does is, if I invalidated the layer 7, it would download all of my dependencies from the internet, from NPM, and then install them. Now, if I've run that once before on my system, it will only have to download the new dependencies from the internet, and it can use that local cache to install the rest of them from that cache, avoiding an extra download and just speeding up the process. And so I'll call that API node 8. And so with that, we have a Docker file that I'm pretty happy with. We took that initial naive implementation and improved it along so many dimensions, both from repeatability, size of the image, avoiding invalidating the cache so that future builds are faster, documentation around ports and the fact that this is a production image, using the production command that makes the most sense, and using a non-root user within the container. Now let's take a look at sort of the image sizes as we progress there. I'll grep for API node. And we can see we started off with those huge images. When we moved to the Alpine-based node image as our base, it cut it by a factor of 5. I believe this small jump was when we added the -- only production option to our npm install command. So there were 30 megabytes of dev dependencies that were previously getting installed. And then the change we made there at the end, where we set the cache for the npm system, saved us a couple of megabytes. And so huge improvements along size, security, clarity. And this is a Docker file that I would be happy to use. Now, if you look in the repo on GitHub, you won't actually see a Docker file in module 5. That's because I've included them here in module 6, and I've got each of the sequential steps that we took improving it with comments describing the commands that we built up along the way. Now that we have a Docker file and a container image for the Node.js API that we're happy with, let's go ahead and shift gears into the Golang API and build one out for that. Now, similarly to with Node, I could start from Ubuntu, but instead I'm going to use the official Golang image. And because we're doing it the naive way, we're not going to tag it. We're going to use that latest. One, and then we'll come back and improve just to see how much that saves in our final image size. But yeah, we can start from that Golang image. And so I can build it with just that from command. This image would be identical to the upstream base image at that point. Like with Node, we want to set a working directory. In this case, I'm just going to set it as app. We need to get our source code into the image. So again, we can use the copy command. Let's just copy it all. We're going for the simple naive implementation first, and then we're going to improve upon it. To get the dependencies installed, we'll use the run command with go mod download. So that will look at our go mod file and download those dependencies. And finally, we can set our command. And for this, I'll use go, run, and then point it at my main.go file. So this should be a functional Docker file. And there we go. Let's do a Docker image ls, and we'll grep for API Golang. Okay, again, over 900 megabytes. Over the set of improvements that we're gonna make, we'll improve that quite a bit. I will add tag 0 to that one just so we can remember it. We never wanna use an untagged or latest image. And so we'll add the 1.19-alpine tag, and then we can rebuild with that. And so already just that has cut our image size in half, which is great, but we're not gonna stop there. Just like how with Node, we didn't wanna run our npm run dev script because that's a development specific thing. Here, go run actually builds and runs our application. And rather than doing that, we would much prefer to build our application in the Docker file, and then at runtime, we can just call that built binary. And so instead, add a run command, we'll do go build -o API Golang. That's going to create a binary called API Golang from our main.go file. And then rather than use this as our command, we can just run API Golang. We'll call this number 2. This change means that every time we start up our container application, we no longer need to build it because it's already built. So we're just shaving off time that it would take in that container boot up process. At this point, I'll also point out the Docker ignore file that I'm using for this project. I've added the makefile, the readme, and any Docker file that I create to the Docker ignore. Those are files that do not need to be in the image. And so this prevents when I make that copy command from invalidating the cache each time I change the Docker file, each time I add something to the readme, etc. Now, similar to Node, we don't want to invalidate the cache here before we download the dependencies, because then we'll end up downloading those dependencies way more often than we need to. And so I'm going to move this copy command after. And instead, we can just copy the files that contain the references to our dependencies. And so that's the go mod file and the go.sum file. And we'll copy those into the current directory. I'll call that number 3. With that change, we can make changes to our source code without invalidating the cache before downloading dependencies. And so each build would be much quicker. And now at this point, we're going to add a new technique that I haven't shown yet. And that's something called multi-stage builds. And these can be super powerful because it allows us to have, within a single Docker file, multiple individual stages that are building separate container images. Now, for a language like Golang that is compiled, this is super helpful because we need a lot of dependencies in the build stage where we're using them to build our code. However, the end result is this binary that can have all of its dependencies statically linked. We don't need any of that Golang toolchain in the final image. I'm going to label this stage as build, and then I can add a new stage down here. And in this case, I can use a special image called Scratch. And this is a official image that we can look at here. Let me just go to Docker Hub. It's a Docker official image. It really has nothing in it. The only thing that it has in it is a valid root file system. It's effectively a no-op that gives us a place to start from that we can copy our binary into. And so now, since we're starting from that Scratch image, we can use a copy command, but in this time, instead of copying from the host, we're going to copy with a -- from equals build. And so now this is saying copy from this container image that was built in that first stage. And now we want to copy the /app/API Golang. And we need to use /app because that was our working directory where that binary ended up. We want to copy that too. I'll just copy it to API-Golang. And so it will be at the root path. And then we can call it from our, we can call that when we instantiate a container from this image. However, that wouldn't work as is because this build command didn't statically compile all those dependencies in. And so I need to modify that build command, and I can do so like this. And so I've added these LD flags to change the link mode to external and set the compilation to static. I've also added this netgo tag. I found that I needed to add that to make my networking within the image work properly. However, by doing that, I now get this compiled binary that has all of those dependencies built in, and I can run it from this Scratch image. And so if I do this and build it, I'll call this one 4. Ooh, but when I built it, I ran into an issue where my build stage didn't have the compiler required to do that static linking. And so one way that I can fix this is to use Buster, which is a Debian-based distribution. My Alpine image, while it was smaller, that doesn't matter as much anymore because this build stage is separate from my deployable stage. I'm going to end up using this image to deploy. And so even if this is slightly larger in my build stage, my deployable stage should still be quite a bit smaller. So let me try building that again. And so that can be a trick when you're using multi-stage Docker files, is you care a little bit less about the size of your intermediate stages. And so you can use an image that has more build tools available or is slightly easier to work with. And so in this case, we're using that Debian-based image in the build stage, and then we're still getting the benefits of that tiny scratch stage for the output. So if I look at the image sizes here, we've now jumped from 500 megabytes to that statically compiled one is only 16.8 megabytes. So huge benefit by using that multi-stage build, compiling to a static binary, and then copying that into a separate stage. A couple of things I want to add to set up my production environment, and that is an environment variable for Gin, which is the API framework that I'm using. And so I'll do Gin mode and set that to release. So similar to node end production, Gin behaves differently whether or not this environment variable is set. And then I know that this app is going to run on port 8080. And so I'll set expose 8080 there as documentation for the end user. I'll build this as tag number 5. And then the final improvement that I'm going to make is similar to the cache mount that I use for NPM, but we can do the same thing for our go mod download command. And so I can add a cache mount here. This /go package mod and the root cache go build are the two directories where those dependencies get cached as they're being downloaded and installed. And so adding this can just speed up subsequent builds accordingly. And so as my final image, I'll call this 6. I guess one final thing that we can do from a security perspective, like our node-based API, we would prefer to use a non-root user within inside the container. And so to do that, we're going to need to set up that user in our build stage and then copy a couple of files into our release stage that will allow us to use it. I can do that with the run user add command, and I'll do user ID 1000, and I'm calling it non-root. Then in my release stage, I will need to copy the password file from my build stage. So I can do copy from build /etc/password. That will copy that in. And then I can do user non-root, and that will use that user. We'll call that number 7. Now in this case, whether that was necessary or not is a little bit questionable because we only have our Golang binary. That's the only thing pretty much in that scratch image. The attack surface area is quite small. And so maybe it's over the top to add this non-root user, but I just wanted to highlight the fact that we can do it, and it provides one additional layer of protection to our sort of defense in depth approach when it comes to security. And so with that, we have a Docker file for our Golang-based API that I'm relatively happy with. Again, we've pinned our base image. We've used a non-root user. We're avoiding invalidating the cache when possible. We're leveraging this cache mount to speed up future builds. We're compiling to a static binary and leveraging a multi-stage Docker file to really take advantage of a much smaller image in the end. And we're setting up our final environment with things like this environment variable and the expose command for the port that we plan to run on. And so with this, we can create a container for our API that's both small and secure. Just like before, if you take a look at the repo, you won't find a Docker file in the module 5. Instead, I have created a number of Docker files here in module 6 that walk through all the steps that we just went through and have commentary around why we're doing the different things that we're doing. So we've got 2 of our 3 applications containerized. We have the Docker files created. The final one that remains is our React client. So let me navigate to that, and I will create a Docker file. And with this one, the development mode for a Vite-based React app is going to be a Node.js server serving those files. And so you'll see that our Docker file looks pretty much identical to the one that we had for the node-based API. So this would be a valid Docker file for that. Again, let me build it. So I'll do Docker build -t. We'll call it client React 0. And we'll build that. As always, before that even finishes building, I'm going to add a pinned version of that base image for repeatability and image size. In this case, we're going to end up using a multi-stage build as well. So I'm going to use a Debian-based base image just because it's a little easier to work with than Alpine sometimes. And I'm not as worried about it since it's not going to end up in the final image. So I'll tag version 1 as the one with the 19.4 bullseye tag. Similarly, our Docker ignore file is going to have the node modules directory within it because we don't want to copy those into our image. Two improvements that we saw with the node API that we're going to make here as well is we don't want to invalidate the cache by copying in our source every time. Instead, we're going to copy in the package.json and package lock.json. And then also, let's set a working directory as /user/source/app. I'll tag that as version 2. Changes like that don't actually modify the size that much of the final image, but it's just useful to see kind of the progression. I'm going to use the same cache mount approach that we used before to speed up future installs. I will use the npm CI command here. I'm not going to use the -- only production flag because in this case, it's our build stage where we're going to generate some static files rather than the final image that we're going to deploy a container with. And so you'll see here, our command is still currently npm run dev. That's going to run a development server. That's not what we want. What we actually want to do is run npm run build, which is going to generate a set of static files, HTML, JavaScript, and CSS, that then we're going to be able to serve. So this will generate those files. I need to name my first stage because we're using that multi-stage build approach. So this will be as build. We're going to add a new stage here at the bottom. And we can use from Nginx. And let's see what version of Nginx we want to use. Let's use 1.22-Alpine. We're not going to need a command. We're going to use the default Nginx command. But in order to make this work, we need to get the files that we built in line 13 and copy them over into this final release stage. And so to do that, we'll use the copy command. We'll specify from build, that's saying from that top build stage. Look at the path user source app. So we have our work directory, user source app, and then the npm run build command is going to place those files in a subdirectory called dist for distribution. And then this path is the location. This is the convention for where you would store your website files if you're going to serve them with Nginx. And so that's what we're saying there. We need one more copy though, and that is to copy in our Nginx config. And so our Nginx config is how we're going to set up Nginx to serve our site the way we want it to. And so this is being copied from the host. I have it here. And let me just walk through this real quick. We've got a few endpoints set up. We've got a ping endpoint, which just returns 200 pong directly. I also have these two additional endpoints set up as proxies. So if you go to /API/Golang, that gets proxied to this address. And if you go to /API/node, it gets proxied to this address. And we're going to set up Docker when we run it to host those two APIs at those paths within the network that we set up. And then finally, the root path, if you don't hit any of those, you'll end up here. It's going to serve our React app files from that directory where I copied them in. The final thing that I'll do is just to, once again, have an expose command. This is just going to be an HTTP server, so we're exposing port 80. That's where it's expected to listen. All right, let me build this as 3. And actually, this Nginx image, the official one, runs as root. And so one way to improve that, as always, is to run as a non-root user. And so there is another image that I've found, which should be pretty much identical to that one. Let me just search for it here. This Nginx Inc. Nginx Unprivileged is a very popular one. It has over 100 million pulls. It's very similar to the official Nginx image with a few minor tweaks around the default settings, including the user that it is run as. And so in this case, I'm going to swap out from that image to this unprivileged image. and rebuild it once more as tag number 4. And one of the key differences when you're running unprivileged is that you can no longer bind to port 80. You can no longer bind to any port below 1024, I believe. And so rather than expose 80, the default here is going to be to run on port 8080. And so I'll change that. And with that, we can build it once more. And let's just look at the image sizes as we progress. So we can do, instead of that, we're looking for client React. We started with a massive 1.16 gigabyte image. Then when we switched to the Nginx image, it dropped to 23 megabytes. The unprivileged Nginx image isn't quite as optimized, I guess. So it's 76 megabytes, but I think the improvement of running as a non-root user is worth it for that extra image size. As with the other projects, within the module 6, I have a series of Docker files listed out here that show the improvements along the way, along with commentary. And so feel free to look at them and see the differences between each step, why we're making the changes that we did. Now, going through that process, hopefully it was educational. It might have felt a little bit repetitive, but that's kind of the point. We want to find a set of general principles and practices that we can apply to any Docker file for any container image that we're building. And the general approach that I think about is, first, we want to make it work. That's kind of the fundamental thing that needs to happen. That's that naive base Docker file that just has a few lines, gets it running. Then we want to think about two things. How do we make this more secure? How do we make it faster to build so it's easy to work with? I've laid out a legend here that talks about the 3 types of improvements that we're making, whether it's impacting the security of the image, the speed with which we can build it, or the clarity of the image, how clear it is for future developers who are coming along and reading it. And so for each of these techniques, I've listed out with the emojis so that you can see what they're doing. We pin specific versions within our build. This can impact security, speed, and clarity. The base image is a huge one, right? If we pin a specific small, secure base image, that's a great starting point. We can either use a tag, like I was using 1.19-Alpine. You can also use the hash of the image itself to use it, or a combination of the two. So you can have the tag and then an @, and then SHA-256, and then the hash. That's actually kind of the best of both worlds, where you have a human readable version as well as that immutable hash that will correspond to a specific version that can't change. You also want to pin specific system dependencies. So if we were installing something from apt or a package manager, we would want to install a specific version there so that it doesn't change on us. That can help with security as well as clarity, so you know exactly what is going into the image. And then application dependencies. So within our package lock JSON file, within our go mod or go sum files, we want to install the exact dependencies every time so that we're not accidentally changing things from one build to the next. I mentioned this in the pinning of specific versions, but it's worth calling out again. You want to think about what's the smallest and most secure base image that I can use that will still be nice to work with, and I can install my app into it. That's going to help both from a security perspective as well as a speed perspective, because those smaller images are just easier to move around. Whenever we're adding a command to a Docker file, we're adding layers. And we want to think about how do we protect that layer cache such that future builds can leverage as much cache content as possible. The general principle here is to order your commands by how often they're going to change. So that base image is very infrequently going to change. We want to install our dependencies before we copy in our source code so that we don't bust the cache there. We want to use that cache mount technique so that it can store downloaded dependencies locally and reuse them in the future. This next one is a technique that I didn't actually highlight in that process. It's a relatively new feature. It's an option to the copy instruction. And by using copy -- link, it creates a new separate layer that's not tied to the previous layers. And this is super useful in the multi-stage build environment. If I'm copying from the previous stage, I can use this such that if I change my base image on my second stage, that won't invalidate the cache, because this copy.link, when I'm copying from that previous stage, it ties it to that layer stack instead. And then the final step is to combine steps that are always going to be executed together so that we have fewer total layers in our image. We also, wherever possible, want to be explicit within our Docker files just for clarity's sake. We want to do things like set that working directory so we know where within the file system we're operating. We want to indicate the standard port that we're going to be listening on with that expose command for clarity. And we want to set the environment variables how we want them with the end instruction so that they'll be automatically set when we run that container. We also want to avoid unnecessary files in the container image. We can do that in two ways. We can add things to the Docker ignore file so that they don't get copied in. We can also, when we issue our copy command, copy specific files or subdirectories rather than just copying in the whole build context. For security purposes, it's always better to use a non-root user, so we saw how to do that in a few different cases. We also want to only install production dependencies, so if there's certain things you only need in your development environment, there's no need to build those into the container image. We always want to avoid leaking sensitive information. And so a good example of this that I'll show here in a minute is if you have a private repository that you need to log into. You could have private NPM packages. Maybe you're building a Python app and you have a private Python registry. We'll need to pass those credentials in a specific way so that they don't get built into a layer within our container image. And then the final one here is just to leverage multi-stage builds where it makes sense. We saw how with the Golang API, we were able to cut our image from 500 megabytes to just 16. With the React client, we were able to go from that node-based build environment to that optimized Nginx image at the end. That saved quite a bit of size and just makes a lot more sense for serving those static files that are generated. As I built out those images, I often chose an Alpine-based base image. I was doing that because of the size. However, size is not the only consideration when choosing a base image for your container. It is an important consideration because the size of that base image is kind of the lower bound on the size of your final built image. However, you also want to think about how well that particular base image supports the language that you're running in. In this case, it may have not been the best choice for a Node.js application. If you look at the official Node.js Dockerfile page, you'll see that Alpine is still considered experimental, and that's because it uses a different variant of the standard C library. And so there can be subtle bugs associated with that if your code or the libraries that you're depending on are making assumptions about the implementation details of that core library. You'll also want to think about the ergonomics of the image. How easy is it to work with if you need to install additional packages? Does it have utilities built in for debugging, etc.? And then finally, the security of the image is another huge consideration. Things like the number of CVEs built in, at what level, and the attack surface area if someone is trying to compromise the container. On the right-hand side here, I've listed out some sample images that you could use for a Node.js application. The first one is the default latest tag, which is currently pointing to the 19.8 Bullseye image. And Bullseye is a variant of Debian. That one is nearly a gigabyte. It has 5 critical vulnerabilities in it. Generally, you wouldn't want to use that. However, it is quite easy to work with. You can use the app package manager to easily install lots of different packages, etc. The next one down there is the slim variant of that. So it's still using that Debian based image. It has cut the size by a factor of 4, eliminated all of those critical, high, and medium vulnerabilities. It still does have some low-level vulnerabilities, CVEs. However, it's a much better choice than the full-size image for that reason. However, because it's slim, it won't have a lot of utilities built in out of the box, and so you may need to install those if you need them at either build time or at runtime. The Node Alpine image is the one that I was using in some of the examples. It doesn't have any CVEs built in. It's quite small. However, as I pointed out, and I actually learned this after filming that section, it's still considered experimental by Node. And so if you go to the repo, you'll notice that I'm using that slim-based Bullseye image for the base image there. There's 2 additional images here at the bottom that I've listed out. The first one is what is called DistroList. That was created by Google as a security-focused image that only contains the language runtime that you need. It doesn't have any additional things like a package manager, shells built in, etc. And so it is quite small and reasonably good from a security perspective. However, one potential downside is that it only supports LTS, long-term support variants of Node. And so if you want to run on a different version of Node, that's not possible. It also, if you need to install anything outside of Node, there's no package manager, so that could be more difficult to do. The final image that I've listed there at the bottom is from ChainGuard. And ChainGuard is a security-focused cloud-native company. They have started producing and maintaining these base images for various languages and runtimes. It is quite small. As you can see, it's the smallest one listed here. It has no known CVEs in it, and it's designed specifically with security and software provenance, where the source of any dependencies are coming from. Because it is more new, and it is really locked down, it may be slightly more difficult to work with in terms of the types of packages that are supported and included if you have particular needs for your application. And so I think as a general purpose image that's easy to work with, the Debian-based variants, the slim variant in particular, is quite a good choice. And if you're really looking to lock down your eventual containers, something like the chain guard based image could be a good choice. Through the process of building out those Docker files for the demo application, I highlighted a number of different instructions. However, I didn't cover them all. There's a couple of additional features that I want to call out here, included this dockerfile.sample in the repo as well. The first one is parser directives. So at the very top of your Docker file, there's two things you can do. One, you can specify a specific version of the Docker file syntax. That's necessary if you're using some of the newer features that are not enabled by default. So that copy -- link that I talked about a minute ago, that I think is in Dockerfile version 1.5. So if you wanted to use that, you would need to have this directive at the top of your Docker file. You can also set an escape character. The default escape character is going to be that \, but if you wanted it to be something else, you could set it accordingly. The next feature that I'll call out is label, and this is super useful for including important metadata within the image manifest. For example, there on line 14, I've included myself as the author of this Docker file. You can add any arbitrary key and value pair. There are a number of standard specific labels under org open containers image that people use, including things like authors, version, etc. So I would suggest taking a look at those and deciding which ones make sense for your images. I also mentioned that sometimes you want to combine multiple commands into a single step, so they're combined within a single container layer. One nice feature for doing that is what's called the here doc syntax. And if we see there on line 20, we have run, and then the less than EOF, apt update, apt install, EOF. That allows us to write multiple commands across multiple lines. However, they get interpreted as being a single line within the Docker file. And so we'll execute those two things in turn, but they'll be stored within a single layer within the container image. In order to avoid sensitive data from leaking into our image at build time, we will want to use the secret mount type. So on line 30 there, I have an example of that where we're mounting in a secret. So in this case, it is on our local system, it's a file called secret.txt, and we can mount that into the file system of the container at /container-secret.txt. And that will only exist at build time. It will not get included in the final artifact. That is an important technique to know if you need to use credentials within your build context. Now, so far, we've been using the CMD or command option, and that specifies the command that gets run when you create a container from your image. There's an additional instruction called entry point, which is slightly different and a bit nuanced as to how these two interact with each other. It can be a little confusing as to which of these gets run in which case. If you're building your own application and it's always going to be run with the same set of arguments, you want to just place all of those in the command like we've been doing. However, if you're building a utility where you can pass additional arguments to the container at runtime, you would want to put the executable in the entry point and then allow people to append arguments via the command at runtime. When we wanted to get files from our host system or from an earlier build stage into our container image, we were always using the copy command. There's a very similar command called add, which is a little more ambiguous. And so Docker generally prefers using the copy command. You may see Docker files though that use add, and just know that they perform almost the same way, but there are a little bit of nuance in the syntax for very specific edge cases. So just know that that exists. And then the final thing to call out is there's a technology called BuildX, which is built into the Docker CLI, which allows us to do a number of things. But one of the very important things is to build and run multi-architecture images. So if I'm on an x86-based system, but you're on an ARM-based system, or I want to deploy to an ARM-based system, I can use BuildX to build versions of my image that are compatible with either of those. Now, I'm not going to go into detail in this course. However, I do have a video that does a deep dive on BuildX and building and using multi-architecture images that I'll link to in that card up there. I will just pull up this dockerfile.sample and just interact with it a little bit though. So within module 6, I've got this dockerfile.sample. And then in my make file, I have a couple of commands that I'll want to show you here. The first thing that I'm going to do is make build sample. Because it's using that secret mount, that's a build kit feature that you have to enable. And so by specifying the environment variable docker build kit what equals 1, I'm able to use that. I'm also setting this base image tag as a build argument. So one important thing to call out is that within a Docker file, I can use this arg instruction. That will be an environment variable available at build time, but not available at runtime. And so in this case, I'm setting my base image tag. It was going to default to 19.4, but I was able to override that with this base image tag here of 19.3 in my build command. However, even though they're not available at runtime, they still exist as artifacts in the image metadata. That's why we can't pass credentials using this build arg approach. Instead, we want to use this secret mount approach. Now you'll notice that I have both an entry point and a command here. And so I'm going to run this image and let you, with a few different options, and let you see how that behaves. And so to do that, I have this run sample entry point command. So I'll do make, which goes off and builds our image. And then it's going to run it in a number of different configurations. If we run the image with no arguments, so if we just do docker run and then the name of our image, what do we get out? We get out, hey team, wave entry point plus command. So with no arguments, we echo both this string and then we get this string as well. So both of those get passed to the echo command. If we run with an argument, so that would be like docker run sample plus argument, now we still get hey team, wave, entry point, but instead of plus command, we get plus argument. So adding that argument onto my docker run command overrode the command that was specified in my Docker file. We also can override the entry point at runtime. And so here, if we do docker run -- entry point echo sample, that overrides the entry point and it ignores our command. And so that comes back with an empty string because we ran the echo command with no arguments. And then the final case is if we override the entry point and we pass additional arguments, it's going to override the entry point, ignore the command, and use the arguments that are passed at runtime. And so with this command, we end up with hey team, overridden entry point, plus arguments. Hopefully that description shows you how those two things interact. Like I said, if you're building your own application that's not going to be called with different arguments each time, put everything within that command block. It's just simpler, and we don't have to worry about the entry point. You're generally only going to use the entry point if you're building out a utility that's expecting additional arguments at runtime to be passed into that container. Now, I do have a make target here to also demonstrate building multi-architecture images. So I'll do make build multi-arch. In this case, I have a repo on Docker Hub called sid palace multi-arch test. So I can show you that. And this is going to, with this -- platform tag, it's going to build one image for AMD 64, one for ARM 64, and one for ARM v7, which is a 32-bit ARM architecture. It's going to build that based on the dockerfile.sample, and then it's going to push it to Docker Hub. So if we go here, it is still building. Once that finishes building and pushing, we would see an updated tag. I last pushed it 20 days ago, but if I update this here in a minute, it will update to now. We can see it's working on those different architectures in parallel. And so behind the scenes, BuildX and BuildKit are using a emulation technology called QEMU, QEMU, to enable us to build an architecture other than the one that we're actually running on. This topic is becoming more and more important as the number of developers on ARM systems with Apple Silicon is increasing, and the fact that ARM-based servers in the cloud are generally quite a bit cheaper than their x86 counterparts. So being able to build for whatever architecture you want can increase the likelihood that your team is all compatible and allow you to take advantage of some cost savings with your eventual deployment. So it looks like it is finished. So if I refresh this, we should see that we just pushed a few seconds ago for all three of these architectures with that test image. And that concludes our deep dive on writing and optimizing Docker files. Hopefully you'll be able to take that knowledge and now apply it to any future application that you'll need to containerize. In this portion, we focused on building out those production container images. In later modules, we're going to think a little bit more about how do we modify these to make them easier to work with from a development perspective so that we can have both our optimized production image as well as a development and debug or test image that we can work with on a day-to-day basis. So far in this course, we've been building all of our container image locally, But if you're working on a team or you need to deploy those containers somewhere, you're going to need to start using a registry. A container registry is a repository or a collection of repositories used to store and access container images. So these are generally stored somewhere in the cloud, and they enable us to take those images that we've built either locally or within a continuous integration server, push them to this registry, and then other team members will be able to pull them. We can pull them into whatever deployment environment we're using. Repos can be either public or private. So when you go on Docker Hub and search for those public images, you'll find those, but you can also set them up such that they require authentication. There's many different container registries that are available. Docker Hub is a popular one that is provided by Docker, the company. GitHub has its own container registry. Google, Amazon, Azure, they all have container registries as well. As I mentioned, you can have public or private container registries. For a public registry, you don't need to authenticate in order to pull. However, in order to push to that registry, you would need to authenticate. And for a private registry, you'll need to be authenticated for both pushing and pulling. Docker Desktop has what's known as a credential helper. And using this, when you log into one of these container registries, it's able to access system resources, such as on macOS. It stores the necessary credentials within your system keychain, so that they can remain secure on your local system. Additionally, some registries may leverage their own tooling to authenticate. For example, the Google Container Registry uses the gcloud command line utility to authenticate your GCP user to that registry and works with the Docker client to provide access. Now, I want to demo building and pushing an image to Docker Hub and the GitHub registry just to showcase how we would do that. I'm using the most simple Docker file you could imagine. Here, it's just going to have a base image from scratch. I'm putting that into a Docker file. I'm building my scratch image from that. And then I'm deleting that Docker file just because I don't want to store an extra file in the repo. So I do make build. We've now built that container image and it exists locally on my system. In order to push to a remote repo, you have to do two things. One, you need to be authenticated to that repo. And two, you need to tag an image with a tag corresponding to that repo. And so if I go to Docker Hub, I've already created this repo called my scratch image. If we needed to create a new repo, you would click the create repository button, fill out the name, add a description, choose if it's public or private, and then click the create button. In this case, I've already created this. And so the tag that we need to use in order to push to this repo is going to be Sid Palace, which is my Docker Hub username, the name of that image, my scratch image, and then we can append additional tags to the end. In order to authenticate to Docker Hub, we would use the docker login command. I've already authenticated, so it used those existing credentials, but it would ask you for your Docker Hub username and password in order to log in if you hadn't done so before. So in order to take this image that I just built and push it to Docker Hub, I need to re-tag it with a tag associated with that repo. So in this case, it was Sid Palace / my scratch image, uniquely identifies that repo. For Docker Hub, you don't need to include a prefix. You can just use the username and repo directly, and it will assume that it's Docker Hub if you don't have a registry prefix in front of it. We'll see that's a little different for the GitHub one. But in this case, I'm using the docker tag command to take my original tag of my scratch image that I applied up here, add an additional tag of Sid Palace my scratch image. And because I don't have a colon with a tag version, it's just going to apply the latest tag to it. I can then push it to Docker Hub and that will show up. However, generally we never want to use the latest tag, and I'm going to talk about tagging best practices here in a bit. But it's much better to apply a specific tag to this. So I'm going to once again take my original tag of my scratch image, apply a new tag which corresponds to my Docker Hub repo. And in this case, I'm adding the tag ABC123 as just an example tag. I can call a Docker push on that tag and it'll get pushed to Docker Hub. So let me just call that make push Docker Hub. It tags my images with the necessary things and then pushes both of those to Docker Hub. I can now go to Docker Hub, and if I refresh the page, we can see both that latest tag when I didn't specify anything, as well as my ABC123 tag were both pushed just a few seconds ago. So that's Docker Hub. Let's now go through the process of authenticating and pushing to GitHub Container Registry. The process looks quite similar, but we do need to follow the instructions at this link. And so here's a walkthrough of how to work with the container registry. In particular, I want to look at authenticating to the container registry. They give some instructions on how to do this within a GitHub Actions workflow. I'm going to use this authenticating with a personal token option. And so the way that we do this, the set of minimal permissions that we need can be created using this URL that they provide. Zoom in just a bit. I'll say Docker course creds. It has the right packages permission. Now I'll click generate token. And don't worry, I will delete this token once I finish recording. So I'm going to export this as my container registry personal access token. Great. And then there was a login command here. Yeah, so I'm going to echo that token out and pass it to the Docker login command, specifying that I want to log into the GitHub containerregistry.io registry. So echo that. Looks like our login succeeded. And now, just like with Docker Hub, I'm going to retag my image using this repo name. And so in this case, I have the same repo name as I had on Docker Hub, but now I'm prefixing it with ghcr.io, which tells it to use GitHub Container Registry. Again, if you don't specify tag, it will default to latest. And then down below, I'm tagging it with ABC123 and pushing both of those to GitHub. So I'll do make push GitHub packages. It tagged both of them, pushed them to GitHub Container Registry. And now I can navigate to GitHub Container Registry, Sid Palace, my scratch image. And we can see we have a latest tag and an ABC123 tag. Now let me just go delete those personal access tokens so I don't forget. And that's under settings, developer settings, personal access tokens, revoke all. So each registry is going to have its own instructions for logging in. So find the instructions from the registry itself and then follow those, and that'll work with the Docker client to store those authentication credentials on your system. Now, I talked about when I was tagging and pushing those images, how if you don't specify a tag, it defaults to latest, and that's generally a bad practice. You want to have descriptive tags that tell you what the image actually is doing. It's also important to note the same image can have many tags. And so, for example, if we go into Docker Hub, when I last checked on January 30th, all 5 of these tags, Ubuntu latest, Ubuntu 22.04, Jammy-22.1130, Jammy, and this specific SHA-256 hash, all point to the exact same image. And so when we're tagging our images, we can put multiple tags that we think will be useful to the end user. Now, ideally, you want to treat any tag, except for maybe a temporary one that you're using for development, as immutable. And by that, I mean you shouldn't create a tag, push it to Docker Hub or whatever you're using for your registry, modify the image, rebuild and tag, and then push and overwrite. That can be a nightmare if someone else is using that image and they could accidentally get the updated version and cause issues within their process. So you always want to treat tags as immutable where possible. The one exception there is if you're doing something locally and building it over and over and running it locally, you might not need to change the tag every time because you know the fact that you're changing it every time. Now, usually your images are going to be built within some continuous integration system. Hopefully that's automated. And oftentimes I'll see people use some combination of a timestamp of when it was built. So maybe like we see up above, that 22/11/30, it was likely built on November 30th. You might put in a build ID from your continuous integration system. So maybe the GitHub action, the ID of that GitHub action. So if you need to go look and see when it was built, you can see the process that happened. The commit hash of the source code. So let's say I'm building an image based on the latest commit to my main branch. I might take that hash from that branch of the latest commit so that I can very easily find where in the code base that build is coming from. And then also, oftentimes I'll see people use a semver release version. So like 1.1.0 or whatever the latest release version is. These can be combined in various forms. When I set up an automated workflow with GitHub Actions in the developer experience portion, I'll tag the images with combinations of a bunch of these. Also, as we saw, when we pushed to a registry other than Docker Hub, we had to prefix the name of that registry at the front end of our tag. Now that we've built our container images and learned how to push them to various container registries, we can move on to running them and configuring them to all talk together within Docker. Up until this point, we've used the docker run command a number of times to run containers from third-party images. We've seen this example with Postgres a number of times. However, there's another way to run Docker containers that is built into Docker, and that's called Docker Compose. Behind the scenes, they do exactly the same thing, but Docker Compose allows you to specify all of your application configuration within a YAML file, and it makes dealing with the container lifecycle much, much easier. These two images here, on the left-hand side shows the Docker run variant. The right-hand side does exactly the same thing, but using that compose file instead. If you're just running a one-off container, I think using Docker run is fine. But for our situation where we have multiple services that need to talk to each other, Docker Compose is much more intuitive and easier to work with. I'm going to show how to do both for our setup, but in most situations, you'll be using Docker Compose if you have an application with multiple containerized services. I'll also point out this GitHub repo called containerized, which you can paste in a Docker run command and it will generate the equivalent Docker Compose file. And so if you have a command that you've been using and you want to convert that to Docker Compose, that can be a very easy way to do that. Now, there's a ton of different options and flags that you can use at runtime with Docker. I've tried to pull out here the most common ones that I use on a day-to-day basis. And let's go through and test these out and showcase what they do. The first one is that -D, which stands for detached, which allows us to run a container in the background. So as an example, I can run docker run ubuntu sleep 5, and it's going to take over my shell until that sleep command exits, and then it will return. So after 5 seconds, it's done. However, if I'd add a -D to that, now it gives me the ID of the container and runs in the background. I can see it by doing docker ps. And here we see that Ubuntu container running my command sleep99 in the background. The next one is the -- entry point option, where we can override the entry point that was defined in the Docker file. An example of this, by default, the Ubuntu image doesn't have an entry point and uses bash as its command. We can actually use the entry point like this to say docker run entry point, override that with echo, and then we'll pass the argument hello. So when I run this, it should echo hello back to the terminal. There we go. The third one there, --env or -e, or --env file is to set environment variables at runtime. So we could do things like pass in database credentials or configure anything else in the environment that we need. To showcase that one, I can do docker run --env myenv equals hello, Ubuntu, and then the command I'm going to run is print_env, which will print out all the environment variables in the environment. You can see it has these 3 environment variables, including the one that I set at runtime. The init flag is an interesting one. Some programs are not designed to be run as process ID number 1, which is what happens by default if you run them in a container. And so if you pass the init flag with your docker run command, instead, Docker will run its own initialization script, and that will spawn your process as a subprocess. So for example, I can run docker ubuntu ps, and that ps command gets executed as process ID number 1. However, if I pass the init flag and run the same thing, we see that this docker init is process ID 1, and my ps command is process ID 7. This is helpful if your application is managing sub-processes itself. Passing the init flag can make it easier to handle forwarding along termination signals from Docker to the container. The interactive flag, or -i, and the tty flag, -t, allow us to have an interactive tty session inside the container. So if I just run docker run ubuntu, it will call bash, which will exit immediately. However, if I add the -it, docker run -it ubuntu, the -i will make sure that standard in remains open, and the -t will give me a tty teletype or shell session within inside the container. And now I have the shell running in the container. We've seen the --mount and --volume options used quite a bit. when we need to persist data outside of the container layer in a volume, so I'm not going to demo that one now. The name option gives us the opportunity to provide a specific name for a container. Otherwise, Docker will assign a random name when the container is started. So I can do Docker run. I'm going to use the -d flag so this runs in the background and doesn't take over my terminal. I'll name the container my container and then pass it the sleep99 command. And this actually shows one downside of using named containers is that you can't have two containers with the same name on your system. So before I could run this, I would need to remove that container. Now I should be able to run this. And now we have that container in the background. If I do a Docker PS, we can see under names, my container. This can be useful if you want to be able to quickly grab the logs from the container. You can now address it with the name rather than the ID. That container doesn't have any logs because it's just the sleep command. But usually I just let Docker manage my naming for me and do it randomly. The network or net option allows us to connect to a specific Docker network. So if I do Docker network ls, we can see the different networks on my system. I'm going to add a new one called my network with Docker network create my network. Now we can see that new my network was just created. And now I can create a container that attaches to it. And if I inspect that container with the ID and grep for network, we can see it's running in my network. Specifying a network like this allows us to create isolated networks for our applications rather than just letting all of the Docker containers end up on Docker's default network in such a way that they would be able to communicate with each other. The platform option allows us to specify which architecture we want to run our container image. Even though I'm on a AMD 64 system, I can run it with this Linux ARM64 v8 option. It went off and pulled the ARM64 version, and then I'm running this dpackage print architecture command, and we can see that it output ARM64. If I do the same thing but specify Linux AMD 64, we get the AMD 64 result. We've already seen the publish or -p option used quite a bit to connect a port from our host system to that of the container. The -- restart option, there's a few different options. You can have always, unless stopped, or never. So if I specify to restart this container unless stopped, Docker is going to see if it exits, and unless I told it to stop, it will continue to try to restart it. So in this case, that bash command, the default for Ubuntu, is going to exit. Docker's going to see that and restart it over and over. So now I can do watch Docker PS, and we'll see this image is exiting and restarting, exiting and restarting. And then lastly, the --rm flag tells Docker that if the container process exit, it should remove that container rather than leave it on the system as a stopped container. This can help alleviate that naming conflict that we ran into before, where the two containers had the same name. If we had used the --rm flag, when the previous container had exited, Docker would have cleaned that up. To demonstrate this, I can run one Docker container named this one will be there. That's going to exit. However, it should still remain in the system as a stop container. I'll now run another one with the --rm flag called this one will be gone. And now if I do a Docker container list -a, the -a is necessary because otherwise it would only show running containers. And I grep for this one, that should find both of them if they existed. However, we only see this one will be there in the listing. There are way more options than this, including this set, which I think you should be familiar with. You may not use these on a day-to-day basis. The first of which is capabilities add and capabilities drop. This allows you to specify which Linux capabilities should be accessible from the container. So this is a security feature where you can, what is allowable within the context of that container. Cgroup parent allows you to specify which cgroup ID your container should be associated with. If we think back to how we can use cgroups to monitor and limit the resources that the container has access to, this is one way to specify that directly. CPU shares is another cgroup related option where you can specify what percentage of the CPU cycles this container should be able to access. The CPU set option allows you to specify which cores specifically. So if you're fine-tuning performance and want to pin a process to only execute on a specific CPU core, you can do so. These next two are related to the different devices that the container should have access to and at what throughput and bandwidth. If we wanted to be able to access GPUs with our container, we would want to use the GPU flag. We can use these health-related options to specify a health check that Docker will use to periodically ping our container and make sure it is healthy. Like our CPU option, we can use this memory option to specify how much memory the container process should have access to. If it goes over that limit, Docker will kill it. We can use these PID-related options to specify how many subprocesses our container should be allowed to manage. The privileged option pretty much overrides all of these other security options and effectively gives the container access to all of the privileges that it could want. The read-only flag specifies that even the container layer of the file system should be read-only. So if you don't need to have write access, you might want to set this as another security precaution. The security opt option allows you to specify either AppArmor or seccomp profiles that you want to use for the container when it's run. And then this last one is not one that you execute at container runtime, but is something you would specify when you're running Dockerd, for example, if you're installing Docker Engine, and that is to enable namespace remapping for the user's namespace, allowing you to map from a non-root user on the host system to a root user inside of your containers. That's just one more layer of defense against a potential attacker. So like I said, these are very useful to know that they exist. However, if you're working on your development system, it may not be as necessary to leverage more of these advanced configuration options. Let's jump over to our editor and configure Docker run commands and Docker compose configs to run our application. And so I have all of the necessary commands to do this stored within the makefile here, and I'm going to walk through how they're all configured and what each of them is doing. The very first thing that we're going to want to do is to build a version of our container image and tag it such that we can use it in our Docker run commands. So this Docker build all make target is calling a Docker build command, and then because I'm located in a different subdirectory, so I'm in the module 8 directory, whereas we know our Docker files are contained in the module 6 directory, and our source code is in the module 5 directory. That's why I'm having to use this file option and pass it a context outside of my current directory. If you had your Docker compose and Docker files living alongside the code, these commands would be somewhat simpler. So this is going to go off, and this first one is going to build my client React Docker file number 3. And so if you remember, as we were building up our Docker files, at one point for the React client, we were using the npm run dev script. And so that's actually using Vite to serve a development copy of our front end. So we're going to build one image with that Docker file. We're also going to use the final React client Docker file where we're copying a built version of our front end app into an Nginx based container image. So we'll have one tagged client React Nginx based on that image. We'll also build our node-based API using the final Docker file that we came up with. And then we'll build our Golang API as well using that final Docker file that we came up with for that one. So let me just do make Docker build all, and that will go off and build those 4 images. I did clear my image cache, so this is going to take some time to build from scratch all of these images. However, in the meantime, I can walk through the Docker run commands that we're going to have to use to spin up these containers. So I'm going to start by creating a Docker network. And so by default, there's a number of Docker networks on the system. Let me just show those now. So if I do Docker network ls, we can see these are all the default networks that are created. We have a bridge network, we have a host network, and we have an empty null network. If I don't specify a network, it's going to get attached into this default bridge network. However, I want to create an isolated network for my application. And so for that, I'm creating a network called my network. So I'll do just that. I can do Docker network create my network. And now if I list them again, we can see my network. And by default, it uses that bridge driver, which is what we want in this case. The first container that we're going to run is the Postgres container. We've seen this command a number of times. The only difference here is that I've added the -- network option and passed it the name of my network and added the restart unless stopped command to tell Docker to restart it if it were to crash. This -d flag will run this in the background. We can see that Postgres image is running in the background. I could look at the logs if I wanted with Docker logs and then the ID. We can see it's started up and it's ready to accept connections. It looks like all of my 4 custom container images have now built, so I can walk through and execute the various commands such that those containers will start up as well. I'm going to start with API node. So I'm going to work from the database forward. So we'll have Docker run. Again, we're going to run it in the background with the -d flag. I'm giving it a name. I'm giving it a name here so that I can have another make target that will clean up those resources afterwards. I'm putting it on that same network so that it will be able to talk to my database. I'm passing it this database URL. And so I've specified that environment variable here. And one important thing to note is that I gave the Postgres container the name DB. And then I've also added this -- link DB option referencing the name of my Postgres container. And that gives me an alias with which I can address my database container. And that is what is used here in my connection URL. I should now be able to run Docker run for my node container. We can see API node and Postgres. At this point, it looks like my node container is crashing for some reason. So let's look at the logs here. Docker logs. So I wonder if this string is somehow getting escaped improperly. So let me try again. Docker stop API node. Docker remove API node. It's because I copied and pasted this in without setting that environment variable. Export database URL equals that. Now, if I run my container, it should be able to pick up that environment variable and pass it in. So I can do Docker ps. It is no longer restarting. And so I should be able to access on port 3000 my API. So let's make sure that is working. And so it looks like my node API is working properly. For the Golang Docker run command, looks pretty much identical to the API node one, except the name is updated and the image is updated. We're still passing that link option so that we can reference the database in the same way. And so let's start up our Golang image. It is now up. Let's switch over. I know that one is running on 8080. Okay, Golang is working properly. And now we need to get our 2 front-end containers. So we're going to have the one running Nginx and the one running Vite. We'll start with the Vite one. One thing to note is that my Vite config inside of Docker needs to be slightly different than my Vite config outside of Docker. Let me just compare the two. So I'll select for compare. And then here I will compare with selected. And you can see when I was running these directly on my host without Docker, I was able to, my proxy was set up to just forward these to localhost 8080. Now that I'm inside of that Docker network, I'm passing the link option. Instead of referencing on localhost, I need to reference them by the alias for that container. So in this case, it'll be API Golang and API Node. And the way that I get this updated Vite config into my container at runtime is via a bind mount. So I'm using the -v option to specify that with my present working directory and then a relative path to client react viteconfig.js. And I'm mounting that to the same location that the other one would have already been located. And this will overwrite the one that was in the container image with the one on my host system at that bind mount location. I'm linking this both to API Node and API Golang because I'm talking to both of them. And then I've referenced my name as well as my image name down here in the command. So I can run this. Okay, it's been up for 1 second. So let's go to 5173, which is where I'm publishing that port. We can see it loading properly. That's awesome. And then the final container that I want to run is going to be my Nginx-based front end, where I took my React app, I built those files, and then copied them into an Nginx-based image. Almost identical to the Vite one, with the one difference being I don't need a bind mount because the Nginx config that I wrote was already designed to work within this containerized setup. I'm also going to port forward from localhost 80 to 8080 within inside the container, which is where that unprivileged user from my Nginx base image is going to bind to by default. I'll run that. And now if I navigate to just localhost 80, or by default, if I don't specify a port, it will default to 80. It is working properly. And so with all these commands, I can now spin up my application and spin down my application very easily. I've added this Docker stop make target that will stop all of those named containers. I've added this Docker remove one that will clean up those stopped containers off of my system and delete those, as well as delete that network. And so I'll do that now. And so now none of those containers are running anymore. In my opinion, having all these Docker run commands with all these different flags stored in a makefile is pretty clunky and hard to deal with, hard to modify, hard to reason about. Luckily for us, Docker Compose exists and gives us a much nicer interface with which to do this exact same thing. So I'll pull up this Docker Compose file. I'll also show you that Composerize tool. So let me just go to Composerize. Zoom in a bit, paste in my command, click output. And so we see my Postgres command gets translated into this compose file where we have our services. In this case, it's named Postgres. We've named the container DB. We're specifying the network. We're passing in environment variables. We're configuring the volume. We're setting ports. We're setting which ports to publish, the restart option, and the image. I've gone ahead and done this for all of those commands that we had, and that generated this docker compose.yaml file. The latest version for Docker Compose is 3.9. So if you're creating a new Docker Compose file and want to take advantage of the latest and greatest features, you may as well specify 3.9. And then within here, I've got one block for each of my different services. So I'll start with client React Vite, and we can specify both an image as well as a build context. And so Docker Compose can handle not only running our containers, but can also handle building them based on a context that's specified. So in this case, it's pointing to module 5 where the source code lives, as well as a Docker file. And here it's pointing to module 6 where the Docker files live, where the Docker file lives. This init true is the equivalent of a --init in the Docker run command. Again, we've got our bind mount here specified for the Vite config. I did something slightly differently with the networking here. I have two custom networks. I have a front-end network and a back-end network. And so because my React app only needs to talk to my APIs and should never need to talk directly to the database, I've specified that those are attached to the front-end network, my React app, and the two APIs. And then I have a back-end network, which my two APIs and the database are connected to. And so that just gives me even more fine-grained control over which services can talk to which. My Nginx-based service looks very similar. The main difference being I'm pointing to a different Docker file and port forwarding to a different port. My Node API, again, quite similar. I will call out, I've added this depends on DB option, and that tells Docker Compose that wait until you've started up the DB container before you spin up the Node container. As I mentioned, the API layer is connected to both the front end and the back end network, so we can have a listing of multiple networks here that this container should be attached to. Pretty much the same thing for the Golang service. And then finally, the DB service, which we're specifying that password. It's only attached to the back end network. We've got our volume mount at the known location where Postgres stores its data. And then we're using that public 15.1 Alpine image as our container image. Down here at the bottom, we specify our different volumes. In this case, I have my PG data volume that's getting used for Postgres, and I specify my two networks. Because I haven't specified any additional data about these networks, they'll use that default type of bridge, which is the desired network type for this situation. Now, with this all defined in this YAML file, interacting with it is super easy. Let's say I want to build all those containers. I can do Docker compose build, and it will look at the different build sections for each service with the context and the Docker file and go off and build those for me. Now, if I want to run them, I can just do Docker compose up, and it's going to run all 5 of those containers and log out to the console from them all with color coding for each. So I can see now I'm attached, all my containers are running. If I then go and load the page, so in this case, I opened up the Nginx-based front end off screen, and we can see the logs coming from the Nginx container, followed by the log from the Golang container where the front end made a request there, followed by the log to the Node container where the front end made a request. And so we can see this can be very valuable and help us to see what's going on within our containers by attaching to the logs in this way. When we did our Docker run command, we could have not used the detached option and instead had terminals connected to everything. But with Docker Compose, it's just much easier to manage within a single terminal. If I wanted to, I could run these in the background with the -d flag. I could do Docker Compose up -d. And we can see it's created all those in the background. If I then wanted to stop, I would do a Docker Compose stop. And because my Docker Compose file is named as such, that's the default. If I named it something else, I would need to pass in a reference to that file with my Docker Compose command, just like when we run a Docker build command. If we have a Docker file in the non-default location, we need to pass that -f flag. And so hopefully you can see the power of a Docker Compose setup like this. You'll be able to go to the GitHub repo, clone it, navigate to module 8, run a Docker Compose up build, and it will literally build all the necessary images and run it on your system. And you'll have this application running in less than 5 minutes. And you can see exactly how everything is configured within this one file. And so this can be a super powerful tool for you and your team in setting up a common shared environment so that it's easy to build and iterate on your applications. When we go to deploy the application and work on improving the developer experience, we'll make some modifications to this and change the config a bit. But I think this is a great starting point that hopefully highlights many of the different options that you'll use when you're running containers for your multi-service applications. Since many of those more advanced runtime options are security related, it seemed like a good time to do a little bit of a deep dive on container security. And this, I think, is my favorite of the memes that I created for the sections of this course. Just because something is running in a container doesn't inherently make it secure. Depending how you configure things at runtime, it may be secure or it may not be. So here, if you specify user equals root, the privileged option, and connect it to the host network, you're removing almost all of the security boundary that a container would provide. And it's about as secure as using that Cheeto as a lock. There's two primary components to container security. The first one is security of the image itself. So as you're building the image, what features are you using and how are you configuring things to make sure that your image is secure? A big part of that are the software dependencies that are installed within your image and what attack surface area exists that a potential hacker could exploit. The other key area to think about container security is at runtime. So if someone were to successfully compromise your container because of some vulnerability that you built in, what would they be able to do? Would they be able to escape the container and move laterally to compromise the host or other containers? Or would they mostly be stuck and confined within the container because you configure the runtime security appropriately? Some of my main things to think about when you're considering image security are how do you keep the attack surface area as small as possible? One way to do that is to use minimal base images. So the smaller your image, the fewer things installed in it, the less likelihood there is to be a potential bug that can be compromised. One great source for secure base images is a company called ChainGuard, which maintains a set of base images specifically with a security focus. As you're writing your Docker file, don't include things in the final image that you're not going to need. If it's not needed at production time, don't install it. Or use a multi-stage build if you need it at build time, but not at production time. Also, after you've built your image, there's a number of tools available that you can use to scan that image for potential vulnerabilities. There's one built into Docker called Sneak. There's another one from Aqua Security called Trivy. Take advantage of these tools to scan your images and see if there's potential vulnerabilities and what level those vulnerabilities are at. This gives you visibility and allows you to choose if you need to patch them or if you're willing to accept having some known vulnerability in your image. We saw this as we were building out our Docker files. Ideally, you don't want to use a root user inside the container. You want to use a Linux user with the minimal set of permissions to accomplish the task at hand. You should avoid building things like credentials into the image itself. You should treat your images as if they're public and inject any sensitive information at runtime. You also can cryptographically sign your images to prove who was the person who built this, and that can be useful to then verify on the other end that an image is what you expect. And finally, as you're choosing which base images to use, make sure to pin at least to the minor version number. If you pin to major.minor but not the patch version, it would allow updates to the patch version, let's say for bug fixes, to be automatically rolled in, but hopefully not incorporate breaking changes into your system. Alternatively, if you really want to lock down the base image, you can use that image hash, which will always refer to the same image. On the runtime side of things, we can both think about the container runtime itself and the configuration options used for each container. If we're setting up the Docker daemon, Dockerd, within Docker Engine, one good tip is to use the user namespace remap option, as described in the docs at that link, to ensure that containers being run are in a separate user namespace than the host system. And then for individual containers, we can set the file system as read-only if our application doesn't require write access. We can use the cap drop all option to remove all capabilities and then add back anything that we might need after that. We can limit the CPU and memory to prevent a denial of service situation where one process is using too much of the resources. And then finally, we can use security options to set either seccomp profiles or AppArmor profiles, both of which you can find more information at in the docs. Throughout the course, I've used a number of Docker CLI commands as we've needed them. In this module, I'm going to showcase the breadth of commands that exist and how you can use the help flag to get additional information. The four main types of Docker objects that we'll be interacting with are images, containers, volumes, and networks, all of which we've seen so far in the course. For any Docker command, we can do docker -- help, and it will give us information about all of the subcommands, as well as a brief description of what those commands do. In this case, let's look at the commands associated with Docker images. Docker images, Docker image help. And we can see all of the subcommands associated with Docker image. We've seen the build command quite a bit. It's how you take a Docker file and build an image from it. The history command shows the steps that were used to build that image. So I have a Docker file here that is just from Ubuntu 22.04, run echo hello, command echo goodbye. And I built that into a image tagged with the tag new image. So let's do Docker image history on that new image. And we can see my command is here at the top. That was the last step in my Docker file. I've echoed hello here as the previous step. And then these steps are the steps that were used to build that Ubuntu base image. So for example, I can do Docker image history on it. and we'll see these steps within that history. And so Docker history can be a good way to explore the steps that were used to build a container image. The inspect command will show a whole bunch of detailed information about images. It can actually be quite overwhelming. So we can do inspect on that same image. And we get this big JSON dump with a whole bunch of metadata associated with that container image. The import command allows us to take a tarball and create an image from it. Honestly, I've never used that before. The load command similarly can take a tar archive that was generated using Docker save on a container and create an image from it. I don't find that very useful. All my images I'm generally building from a Docker file. Image ls will list all the images on our system. And so as you can see, I have a whole bunch here, some with tags, some without tags. Prune is a great way to clean up those old images. If I wanted to clean up my images, I would do Docker image prune. It would remove any image not associated with a container. That's what it means by dangling images. I'll skip that for now. The pull command we've seen is how we can pull an image from a registry. We haven't used it directly that much because when we do a Docker run, if the image doesn't exist, it will first execute a pull. But if I did want to execute that, I could do Docker image pull and then an image name and tag, and it would go off and pull that from the registry. Push, likewise, pushes our built images to a registry. We've seen that one quite a bit so far. If I want to delete a single image, rather than using prune to delete them all, I can delete just one with Docker image remove, new image, for example. Now it's untagged and deleted from my system. The save command can take an image and dump it out to a tar archive. This could be useful if you wanted to be able to explore the file system outside of a container. I haven't found this to be that useful in my workflows. And then finally, we can use the Docker image tag command to tag an image with a new tag. So I could do Docker image tag Ubuntu 22.04 my Ubuntu tag Docker image list grep my Ubuntu. And we can see I now have an image which is based on that Ubuntu 22.04, but it has my custom tag associated with it. We saw this when we built the image with one tag and then tagged them with new tags to push them to registries in the container registry module. That's it for the subcommands of Docker images. However, there's one more command that's associated with images that's not a subcommand, and that's Docker scan. So I can do Docker scan. Let's just scan the Ubuntu image for fun, 22.04. And that will use a tool called SNCC to go off query a vulnerabilities database and assess whether there's any known vulnerabilities within that image. It then outputs a report of all the different vulnerabilities that we've found. Things like systemd, OpenSSL, these are at the medium severity level. We've got one here at the high severity level. It also tells you when in the upstream project that vulnerability was fixed. So then we can decide, do we want to use this base image or do we want to pick a different one that potentially has this mitigated already? That covers most of the things that you'll be doing when interacting with images. Let's look at the options for the Docker container command. Now, as you can see, there are many more subcommands for Docker containers than there were for images. I'm just going to highlight a few that I think are useful to know. The attach command, if you have a running container already and you want to attach your local shell to the input, output, and error streams of a container, you can do that with attach. A similar one to that is the exec command, where rather than attaching to an existing stream, you're going to run a new command within the container. Just like with images, we can run the inspect, which will dump a big blob of JSON metadata that can have useful information. The stop and kill commands are how we can either gracefully or non-gracefully stop a container. So if you have a container that you've tried to stop, but it won't die, you can always use kill, and that will generally do the trick. You would want to issue that with either the name of the container or the ID of the container. So if we do Docker run Ubuntu sleep 999, now that's going to sleep for 1,000 seconds. And even if I do Control C it, nothing's going to happen. So if I want to get out of that, I can do Docker PS We see that container here is running. And then I would just generally do docker kill, paste that in. And now our container's exited and we've got our shell back. If you want to view the logs of a container, you would do docker container logs and then either the ID or the name of the container. If you want to trail the logs, so if you want to have a live feed of them, you can add the -f command. This container here that you've seen pop up when I do docker ps, it's a system container that you'll likely see on your host, but let's just check the logs of it since we're here. We can do docker logs of that container. We also can do docker container logs. Those are the same command. And then finally, if we wanted to tail those logs, we can add the -f, and now any additional logs would be printed to the console automatically. The ls command lists all running containers, and I believe is pretty much identical to docker ps. If we add a -a flag, it will show stopped containers as well. So without the -a, it's only running containers. With -a, it shows stopped as well. If we wanted to clean up all those stopped containers, we can issue the prune command, or if we wanted to remove a single container, we can use the rm command. The run command is one we've seen over and over, where we're creating a container from a container image. Top can also be a useful one if we want to see what's running inside the container. So let's do a docker run -d ubuntu sleep 99. And now we have this container ID, docker top, docker container top, then ID. And you can see the processes running inside of that container. And then finally, the wait option could be useful if you're writing a script where you needed the one container to finish before you progressed. You could issue a docker container wait command, which would stop your script until that container exited, then print out the exit code, and you could proceed on with your script from there. The volumes options are much simpler. We only have these 5 options. We've seen the create option where you just pass it a name, docker volume create my volume. We can use the inspect volume to look at that. We can see where it's mounted within that virtual machine file system, the name, the driver, etc. The ls command will list all available volumes, docker volume ls. We see a few named volumes here at the bottom, but we also see a bunch of anonymous volumes above it that are created and managed by Docker. If you have data that you want to persist, it's much easier to manage if you go with a named volume, create that volume, and then mount it into your container at runtime. Just like with images and containers, we can use the prune command to remove all of our unused volumes, or the rm command to remove one or more volumes. Now finally, let's look at the options for networks. They'll look very familiar given that they're almost identical to the volume options. Docker network. Just like with volumes, we can create, inspect, list, prune, and remove. The 2 new ones here are connect and disconnect. And so if we had previously created a container, but we forgot to connect it to the network that we wanted with the -- network flag, we could then run a Docker network connect with the ID of the container to tie it into that network. So we can do Docker network ls. Let's say, for example, we wanted to do Docker run Ubuntu sleep 99. I'll run that in the background. But we didn't want it to be on the bridge default network. Instead, we wanted to connect it to my network so that it'll be able to talk to other services that were spawning there. We can do Docker network connect my network, pass it the ID, and now if we inspect my network, we can see the listing of containers that are active there. And we have this one named Awesome Brown. Just to confirm, Awesome Brown is the automatically generated name for that sleep container that I created. If I wanted to remove the container from that network for whatever reason, I could use the Docker network disconnect command. Generally with these networks, because I'm bringing containers up and down so frequently, rather than starting a container and then attaching it, I would just want to add that to my Docker compose config or as an option in my Docker run command so that it would be connected to the proper network at runtime. Now that we're fully versed in the Docker CLI, how we can make the developer experience working with containers extremely nice. What are the main considerations that we should think about in terms of the developer experience when building out applications like this? How do we go from this confused, frustrated developer at the top to this excited pair of programmers here at the bottom? We want an easy and simple setup. We want to be able to iterate without needing to rebuild the container image. So far, even if we made the tiniest change to our code, we would need to rebuild the container image and then rerun the container to have that reflected. And that's just a terrible experience. That being said, we can use the bind mounts that we learned about to mount our source code from our host system into the container at runtime. And then we can use hot reloading utilities like nodemon, or there's one for Golang called air, such that with each change of our source, our applications will get automatically rebuilt and restarted. And those changes will be reflected immediately. We need to be able to debug our code as if it was running locally. And for that, we can add debugging utilities into our development image and set up a special Docker Compose file to use those utilities. We also want to be able to execute our tests within the container. Again, I can make a custom Docker Compose file that we'll use to do that. In most scenarios, the only containers that you'll be building on your local system are the ones you're currently developing on. For production images, you'll want those built within a continuous integration pipeline. And finally, it can be super powerful to be able to spin up an ephemeral environment with each pull request that you make that will have all of your modifications built into it automatically that you can share with a team member to get feedback and iterate on things more quickly. When we get to that, that's where our sponsor of today's video, Shipyard.build, comes into play. They make it very easy to take your Docker Compose setup and get a fresh ephemeral environment built and deployed automatically with a simple GitHub event like a pull request. So let's jump over to the code editor and take our initial Docker Compose file that we built a few modules ago and modify it to improve the developer experience in these ways. So we first built out our Docker Compose file in module 8. So I'm going to copy that into module 11. Let's just make sure it still runs. I already have a make target set up that we'll call compose up. And I'm going to name this Docker Compose dev, make compose up build, which will look at that dev compose file, build my images, and then run them. It looks like line 9 here, where I'm using my present working directory. It's no longer a valid reference to that vite config file. Instead, I'm going to have to set the relative path to that like so. Okay, so things appear to be working as expected. Just had to make that one tweak to the volume mount. I would say if we're thinking of that wish list that I just had up, easy and simple setup is a check. We're able to get up and running with just that single command. Now we want to improve upon iteration without having to rebuild the container. Also, while this volume mount syntax works, I slightly prefer the more verbose version that we can specify here with a type, a source, and a target. So this should do exactly the same thing. And now, in addition to bind mounting in that configuration, let's also bind mount the entire source code directory. So that's going to be in this module 5, client React. And so this will bind mount the client React directory into our container at user source app. One additional point, though, is that within client React, we have things like the node modules directory and the distribution directory, which we don't want to get bind mounted in. And so the way that we can overcome that is to specify another volume mount that has no source and only a target. And so by doing this, it will effectively overwrite this bind mount for this particular path and avoid bringing those node modules from my host system into the container. And just to remind myself what the command is for Dockerfile 3, let's go look at that one. Client React, Dockerfile 3. This is running npm run dev, which in turn calls vite. So we should have hot reloading built in. And so now with these bind mounts in place, let me start up my application again. Now if I navigate into my source code and make a change, let's see what happens. Client React, source, app.jsx. Save it. Because we're bind mounting that source in, we automatically reload our application with Vite, and that gets built in, and we see it immediately on the front end. Now let's take the same technique and apply it to our two API servers. Here we're going to use the same bind mount approach for the Node API, including the empty volume mount over node modules to avoid bringing those into the container. And I'll put it right after init true. Instead of client React, we want API node. And let's just remind ourselves what this Dockerfile 8 is doing. Okay, so we're going to want to make a few tweaks here. This Dockerfile is optimized for our production deployment. But in this case, we want to have a separate build stage that we can target for this development environment. I'll start by naming my first stage as base, and then where we diverge from our production versus development is going to be at this step where for production, we only want to install the production dependencies. So I'm going to say from base here, and then I'm also going to have as production, and then I'll do from base as dev. And so now within this stage, we can have our development commands. So development commands are going to look similar, but instead of npm CI only production, we'll do npm install, and that will install both dev and production dependencies. Let's also move this environment variable down such that we set that only in the production image. After we've installed our dependencies, we want to copy all of our source code in. And then for the development stage, we want our command to be npm run dev. And I'm actually going to call this Dockerfile number 9, just so we can keep track of them. So we have our dev stage where we're installing development and production dependencies. We're copying our source, we're running npm run dev. And then we have our production stage where we are doing what we were doing before with the non-root user, installing only production dependencies, etc. Now in our Docker Compose dev, let's use that new Dockerfile 9 and see if we succeeded. Oh, one thing I forgot to do is in addition to a context and a Dockerfile, you can pass a target, and that allows you to specify which of your stages in your multi-stage build you want to target. So in this case, it would have defaulted to production as the final stage. I want it to target that dev stage because that's going to be where we're running NodeMon for the auto restart. So now let's make a change to our Node API source. Here, source, index. In our response, let's just add, ta-da. So we save it, now refresh, and we see our node reserver was detected, NodeMon saw the change, restarted, and now when we hit that API from our front end, we get the updated version back. And so we've got hot reloading working for our front end in Vite, as well as our node-based API. Let's do the same for Golang. Our bind mount setup should be quite similar. A volume, going to API Golang. We don't need the node modules mount. Depending how you have your Go path set up, that will determine where you're going to install your dependencies on your host system. In this case, it's outside of my project directory, so I don't have to worry about shadowing that with an empty volume. However, my target inside the container, instead of user source app, If we think about the work directory that I used in the Docker file, it's just /app. And now I need to do something similar to my production Docker file, add some development stages so that I can have both my production ready and my development images. Make a new one called Dockerfile number 8. Make sure we're using the new one. And we're going to add a target of dev. And we will get around to adding that here. So my first stage already has a name, but now because I'm going to split this into 2 build stages. So I'll have build base as this. It should be the same up until here, where we download our dependencies. However, this is where we want to split. And so I'll do from build base as build dev. And so for our dev build, in addition to pulling in our dependencies that we've specified, there's 2 more dependencies that I want to add from a development perspective. And that is a package called air, which enables hot reloading. So it'll detect a change like nodemon, rebuild that application, and then restart it. As well as a package called delve, which allows for remote debugging that we'll set up so we can set breakpoints and connect to our container remotely to investigate the state of all of our variables and that sort of thing. And so the command to install those 2 dependencies is go install, pass it the name of the package, and go install, pass it the name of the package. We still need to copy in our source code, and then we'll set a command using that air package. So we'll call air-c and pass it this default air.toml, which I created ahead of time. And it just tells it sort of things like where the main file is, what command it should run when it needs to rebuild, where to look for changes, etc. And so that can be our build dev stage. That will be, actually, I'll just call it our dev stage, like we did in the Docker file. And then for the remainder, we build our production images and then copy them into that final scratch image. So I'll do from build base as build production. Then down here, when we copy from build, instead we're actually copying from build production. We'll add this non-root user within the build production stage. And so that should be good. We're now targeting our dev stage. We're bind mounting in our source code. We're using that air package to do automatic reloading. Let's try it out. Okay, it looks like our app has started up. So let's load here. We can see it's running. Let's make a change to our Golang API just to see that rebuild happening. If we go up to module 5, main.go, and add something here, we see it detected main.go is changing. It just rebuilt. And so if I reload, we get Golang woo. Awesome. I'll save it again. You can see it's detected it, it builds it. When I refresh, that update is reflected. So now we've got hot reloading within our containers by bind mounting our source code in, and then using utilities like nodemon, vite, or air to automatically detect file system changes and update our application in real time. Now, the next item on our wish list is remote debugging. So we want to be able to run a debugger within our containers and then connect to it from our development environment. As much as we love doing printf debugging, where we put in a bunch of print statements, sometimes you really need to use a debugger and investigate a little more thoroughly. And so let's get that set up now. What I'm going to do is create a new Docker Compose file that I'll call Docker Compose debug. And one interesting feature of Docker Compose is that you can take two files and pass them both into the Docker Compose up command. And it will take the first file and then take the second file and overlay it. You only have to define the fields that have changed between the two. You can have your base configuration and then slot in slight differences. And so in this case, we're going to be able to leverage that Docker Compose dev file almost entirely, but we'll add a few new fields, mostly adding additional ports to publish because we're going to have to connect on new ports that the debugger is listening on, and modifying the command that's executed when the container started. We'll start with our version of 3.9, services. The services that we're modifying here are the API layer. So we'll have API node and API Golang. We want to override the command field. So we'll have a command here. And so instead of npm run dev, like we were running before, we actually want npm run debug Docker. And I added that as a new npm script, so we can go take a look at what that is. npm debug Docker runs nodemon, so we still get that hot reloading, but the -- inspect command tells Node to run its debugger. Here we're listening on all hosts on port 9229. So this will enable us to connect from our local host system on port 9229 as long as we publish 9229 in our compose file. And then we're passing it that index.js file as the entry point for the program. So here we'll do ports, and I'm going to have both my normal 3000 port that I had before, as well as my new debug port. And so when I run this command, if I do a Docker Compose debug build, I do Docker Compose, and then I first pass it my development compose file. So that's my Docker Compose-dev. And then I pass it my debug compose file, Docker Compose-debug. And Docker Compose takes those two and interleaves them together such that these will be the new values, but we can still take advantage of all this additional config here. Our Golang API will be somewhat similar. The debugger that we're running for Golang runs on port 4000. It's a tool called Delve, which was that other dev dependency that I installed. And our command, I'll just copy and paste it here because it's a little bit long. Uses that Delve utility in debug mode. We pass it the main.go file that it should run. We tell it which port we want to listen on, as well as some additional configuration options. And so that should be enough to run our application in debug mode. So I can do make, compose, up, debug, build. As I showed, it passes the dev file first, then the debug compose file. And so while that's building and setting up, I can show you the launch.json configuration that I use. And that is the way that VS Code sets up its debugging utilities. So under the configurations block, I have two of them. I have one set up for Node with port 229, one set up for Golang on that port 4000. The key things to call out here are that I'm using the request attach mode because my container will already have that debugger running inside. I don't need to spawn a new one. I just want to attach to it. And then this local root command tells VS Code where the root of this project is within my workspace. And that's so that when I create a breakpoint, it's able to map that to a path within the container, which I'm passing here, of user source app. Oh, I see I hit an error here. It's because I forgot to change this port for the Golang API to 8080. So let's try that again. Similarly for Golang, we're using a particular adapter that is associated with that Delve Again, we're using the attach request option, specifying the port, giving it a remote path. And then this one was a little more tricky to get set up. Again, we need to be able to map from our host system into the container such that it's able to know when we set a breakpoint what that corresponds to and properly apply it inside the container. And so the substitute path command takes the path on the local system and modifies it such that it gets fed in properly inside the container. My app is now running in debug mode. I don't have any breakpoints set or anything, so it just loads as normal. However, I can go into the run and debug portion of my code editor and pick one of these. So let's pick attach to node. Click the play button. Aha. It was not connecting because it was forwarding my debug request to port 3000 where the app is listening. And so instead, I should be forwarding to the port where the debugger is listening. Now that the APIs have started up, I'll click play. And now it did successfully attach. We have our breakpoint in our source code just before it sends that response back. If I reload here, we see it caught at that breakpoint, and we can see all of the local variables, including the response itself, Wednesday, February 23rd, API node 125.07. So if I then click skip over the breakpoint or play, it will resume and allow that to be returned from the API. So let's click play, and we see we got back that response. I'll click disconnect here, and let's try the same thing with Golang. Click the play button. Looks like we were able to attach. Let's load our Golang API. And set a breakpoint somewhere within our Golang code under main.go. Let's do right before we send back our data. Breakpoint. We can see it being injected here in the logs. And now, if we load the page, once again, we successfully caught at the breakpoint. And we can see the locals here. We have our time data as well as our gin context. And now we have debugging working for both the Golang and the node-based API. I also added a React query debugging tools as a dev dependency that get built in here. Allows us to get all sorts of information about the queries that React query is making to the backend. So for example, if we load here, we can look at this query, when it was last updated, the data that we got back. We can tell it to refresh the data. And so without having to reload the whole page, we can interact with the React query specific components directly. That gives us debug capabilities for all of the services that we're building. So that's awesome. And now the next thing on our wish list was to be able to execute tests inside the containerized environment. Similar to how we had a overlay compose file for debugging, I'm going to make us another one called Docker Compose Test. We don't need the port access. We will be overriding the command. We'll just execute our npm run test script, which will execute jest, which in turn looks for our test. So I can just show you the test suite that I have set up. It's quite minimal. So API node, test. We have one example test that expects true to be true, so that's always going to pass. And the package.json specifies test, just calls jest, which will discover the test and execute it. And then for Golang, similarly minimal. I have a test module with example test.go. It tests that 1 equals 1, which indeed it does. And my command that I'm going to use there is go test. So here, instead of using delve, I'm going to run go test, and then I'll pass it this -v option, which will enable it to properly discover those tests. So now, in order to run this, I have 2 make targets set up, or I have Docker Compose calls for Golang and Node separately. So again, I'm going to use the dev compose file first, overlay that test compose file onto it, and then I can specify run build and a specific service within that compose file. And so this one should execute the Golang tests, and this one should execute the Node tests. So if I do make run tests, it's going to build those images and execute those tests. So we see the jest test passed, and let's go find here's the Golang test here. So the Golang test passed, the jest test passed, and we were able to execute those tests within the containerized environment. The next item on our wish list was continuous integration. And so that essentially refers to this idea, whenever you're pushing code to your version control system, you should be running pipelines to do things like execute your test suite, build and push your images, etc. GitHub Actions is a continuous integration system that's built into GitHub, and you can just add a couple of files to your repo, and it makes it very easy to set up this type of thing. I've added a workflow to the repo that I can show here that is going to do a few things. It's going to build our image, it's going to scan it, tag it, and push it to Docker Hub. I'm only doing this for one of the services, just as an example, but you can use the same concepts to add it to as many services as you want. Within the repo, you place GitHub Action files at the .github/workflows directory, and then any YAML file in here will be interpreted as a workflow. With about 50 lines of code here, we're able to configure a GitHub action that will build our images, scan them, test them, etc. So within this file, we have a number of different sections. I'll just walk through them now. This first section, starting with on, tells GitHub when it should run this workflow. In this case, I've specified you want to run it on push events to specific branches and tags. So if I push to the GitHub action branch, which I'm on now, it will trigger this workflow. Or if I push a git tag starting with the letter V, so maybe it's vx.y.z, so some Semver version when I do a release. You can also do other types of events like a cron string, so you would run it periodically based on a schedule, or upon creation of pull requests. Below this, you define your job section, where you have the different jobs that you're going to run. And then within each job, you can have a number of steps. And so I've only defined a single job, which is going to build, tag, and push my image. You specify which runner you want to run on. I'm running on Ubuntu latest. And then the steps that I'm going to run are executing first checkout, which is a public action provided by GitHub, which checks out the code. I then am using a public action from Docker to generate a bunch of tags that I want to use for my image using information such as the name of the branch, the name of the PR, the version. If I'm pushing a tag, I can use that to generate a Docker image tag. And then finally, I'm using the date and the commit hash as another example of a potential tag that I might want to use, like I talked about when we were looking at container registries. Here, I'm giving it the name of the repo that I'm going to push to. And these actions, these public actions that I'm referring to, are available in the GitHub Action Marketplace. And so this was an action that was produced by Docker. You can see the source code here for it. But if we go to the Action Marketplace, we can see here it is. It tells us all the different ways we can use it, the types of inputs, the types of outputs, etc. And so I'm able to specify that this step should use that action, give it these types of tags, and it will automatically generate those for me. Next, again, I'm going to use a public action from Docker to log into Docker Hub. And within my repo, I can specify my username and my access token such that it's able to do that. So within the repo under settings, under secrets and variables, actions, you can specify environment secrets or repository secrets. And so here I've specified my Docker Hub username and an access token such that that action is able to log in. Next up, again, another public action from Docker. So really I'm leveraging their work to make my life super easy. This one is going to point to the file that I want to build, as well as the context with which I want to build it. I'm saying I do want to push it to Docker Hub, and then I'm using the output of my metadata step here and applying those as tags. So this is going to be a listing of all those tags that were generated. This will apply them all and push them all. And then finally, I'm leveraging a tool from Aqua Security using their vulnerability scanner to look in the image for any critical vulnerabilities. You can specify what level you want to block on here. And so I'm saying if there's any critical vulnerabilities in the image, fail the run, and that way I can go investigate. If there are no critical vulnerabilities, it will pass the run. So I haven't made any changes on this branch, but I do want to trigger a run. So I'm going to do an empty commit. I'll do git commit -m empty allow empty git push. And now if I go to my repo under actions, we can see that empty commit just triggered a build. Here's my job. If I click into it, I see it starting up that runner. And then each of my steps, we can see it's checked out my code. It's generated the tags. So let's look at the tags that it generated. We've got GitHub action is the branch I'm on. Latest is just the default. And then this is today's date, as well as the short hash from the commit. We successfully logged into Docker Hub. We then successfully built and pushed our image. We ran the scanner and found no critical vulnerabilities. And then there's just some cleanup at the end. So now let me go to Docker Hub. We should be able to see for our API node repo, this version was just pushed a few seconds ago. And so that kind of highlights the continuous integration workflow that you would want to set up for your container images. That's just a taste of what you can do with GitHub Actions and with continuous integration pipelines. Brett Fisher has a repo called Docker CI/CD Automation that has a whole bunch of really cool examples around doing things, not only building and testing and pushing your images, but actually interacting with PRs, adding comments to those PRs with the results of the tests and that sort of thing. You can see his talk that he gave on this on YouTube. I would definitely suggest checking that out. Now, the final topic that I want to cover here in the developer experience section of the course is ephemeral environments. Ephemeral environments are this idea of building and deploying short-lived, isolated environments that we can use for any sort of purpose, including testing, validation, QA, etc. And in particular, I'm going to use this platform from Shipyard to very easily set up this for our sample application. I'll start by just walking through their onboarding process, and then I'll show you with just a few lines of configuration to our Docker Compose file, we can have ephemeral environments set up with every new PR to the repo. I'm here on the shipyard.build website. I click login. It'll ask me to log in with my GitHub. I'll do that. You'll authorize Shipyard to access your account. This now redirects me back to the Shipyard site, where I will connect my GitHub organization. So that initial connection just gave them access to my user information. Now this is the authorization to actually access my repos. You can choose either all repos or only select repos. So here I'm going to pick the specific repo that we care about, which is the Docker course repo. This will grant them the necessary permissions to read the contents of the repo. They also have features where they can provide information back on the GitHub interface. That's why it has read and write access to checks, commit statuses, and pull requests. At this point, I'll just click install. Now, as we can see, we're on the free trial period. As I mentioned during the introduction, students of this course have an exclusive promotion code where the first 300 people to sign up can get an extended trial period. So go check out the description for more information on that. And then at this point, we can click this green button to add our first application. We'll select the repository that we care about. It's our Docker course repo. And for our base environment, I'm going to use the main branch. We can use the default name for our application. And now if we click the Select Services button, it's going to scan the repo for a Docker Compose file. In this case, because of the structure of the repo based on the course, it wasn't able to find specifically which one we want. I'm going to choose the one that we set up initially in Module 8 because that's the simplest Docker Compose file that contains all the services we care about. I'll just click Select. And now we need to pick which of the services in that Docker Compose file we want to include here. I'm not going to include our Vite-based deployment. Instead, I'm only going to have the Nginx-based front end. We'll leave on our two APIs in the database here. And then we can see that it automatically detected our named volumes. And an interesting feature here is that because we have that named volume, whatever's stored in that volume on our main environment will get snapshotted and copied over to additional environments as we make PRs against that. At the top here, it's saying, please include at least one service with a route. And so we need to provide Shipyard a bit more context and configuration so that it knows how to route traffic to our various services. And the way that we do that is by adding labels to our Docker Compose file. So let me jump over to the code editor and add in just a few lines to our Docker Compose file so that Shipyard will be able to properly detect and utilize those routes. And so each of our services, we can add a labels field. And so here under the Nginx client React Nginx field, I'll add a labels target and add these two labels. The first one is specifying that this is the primary route. This is the route that we want traffic on the route path to come into. And then we're specifying the route as just the /. So this is saying this is going to be the default service that we want you to route traffic to. And so with those two things, that's good. We'll adapt for our API node service. We'll add this. This is not the primary route, so we'll get rid of that. And we will add this going to /API/node, just like we had before. And then similarly for our API Golang, we'll go here and just replace node with Golang. And so with just those, I think it was additional 7 or 8 lines of code into our Docker Compose file, we can now commit that to the main branch. Push it. Now if we go back to Shipyard and reload our latest commit, now we can see that it automatically picked up those labels and is including those in the information about our configuration here. With that, I'll add environment variables. All the default values here should be fine. We don't need any additional environment variables, and click Create Application. This is now automatically going off and building all the containers based on the latest commit to that main branch. It will then bundle them up and deploy them. Now you'll notice that the first time you log into Shipyard, you'll get this message at the top. That's because it's provisioning a standalone Kubernetes environment for each customer, and that allows for isolation between customer data. However, it does take a few minutes to set up, and so the very first time that you're here, you'll have to wait about 10 minutes. After that, the build and deploy should be much quicker. Now, while we were waiting, I realized that I should have added one additional configuration here for our API layer. And so that is the Shipyard route rewrite label. And this is saying if we hit the URL /API/node, our node service is expecting that to come in at the route path. And so by adding this label, it will strip out that prefix, and we'll do the same thing for Golang, because the routes that I've defined inside of my services are not expecting that prefix. So I'll add those and push them. Now, another neat feature that we can turn on is if we go here to this three-dot menu and click under Configure, under Notifications and General Settings, we can add GitHub commit checks and GitHub PR comments so that when Shipyard has information for us, it will populate that back into GitHub so that we can see it from there. We also can tell it which pull requests we want to deploy on. So we could have specific labels. Let's say we only want to deploy on bugs, or we only want to deploy on enhancements, or we can specify a regular expression to decide which branch names we want to deploy with. In this case, I'm going to leave these as the default, so it should deploy any PR back to the main branch. I'll click Save. There's also a Slack integration you can use to get updates and notifications from Shipyard. I'm not going to go into that now, but I just wanted to call it out as an option. A few minutes later, back on our home application page, we can see that our base environment has built and is ready to be visited. Now, you'll also see this little timer here that says stopping in 2 hours and 49 minutes. So that's a feature that is called SLV, or since last visit, and you can configure that within your organization to tell Shipyard how long an ephemeral environment should live. And by putting environments to sleep if they're not being used, allows you to have more ephemeral environments on a given tier within their platform. If I click the visit button, it's going to take us to this page where we get a login prompt so we can log in either using GitHub or Google for OAuth. And this allows you to have these ephemeral environments not public on the internet, but actually protected behind this login layer where you can very finely control who has access to it. So I'll click to log in with GitHub, and we can see we've got our application running within their environment. And if you look up here at the URL, we see our custom URL that's associated with this particular ephemeral environment. Now, if we wanted to grant access to this, we could go to the Visitors tab. And under here, I can add GitHub usernames or Google usernames. And that way you can control who has access via single sign-on. So that's our base environment. Now let's make a slight change to our application and then redeploy based on a pull request event. I'll go back to my code editor and let's have it deploy with a different message on that home screen. So I'll go into my example web application. Here on the front end, in my app.jsx file, I'll scroll down, and instead of hey team, we'll say hey team from Shipyard. And we'll change the wave into a ship. Awesome. Now I'll do git checkout -b Shipyard demo, and I'll commit to this new Shipyard demo branch. Change message. Now I'll push that. Now if I go over to GitHub, I can see that recent branch had a push. I'm going to create a pull request from that branch back to the main branch. If I click create pull request, and now jump back over to Shipyard, we can see it immediately detected that pull request and is now building a new ephemeral environment specifically for that new Shipyard demo branch. Once it finishes building, we'll be able to see that it's different than the original ephemeral environment with that updated message. Clearly, a change that small is quite trivial, but it could represent any number of complex changes to our different services. We could be changing the API layer. We could be changing our things like our database schema. Let me go here to the build details dashboard and show you how that's progressing. It shows us the various services that we have within our application that we selected initially. We can see the build logs as it ran our Docker build commands and looked within the Docker Compose file, found the corresponding Docker files, and built those out. We can see all the logs here across our different services. Now under the Deploy tab, we can see the pods as they come up. And then under the Run tab, we can see the logs coming out of the containers themselves. It's now handling that final DNS setup so that we'll be able to access the environment. And now we have our second ephemeral environment live. Let me visit that one as well. As we can see, it's taken that change that we made in that PR and deployed it in a separate environment from our base environment. There's an additional interface here. If we click terminal, it'll pull up a way for us to get additional information about all of our environments. So we've got our main environment, we've got our Shipyard demo environment. Let me just click into the main one, and we can see the pods running here within that environment. I can choose one of them. If I select it, we'll get the logs here at the bottom. We can also hit the R key if we wanted to exec in and do some debugging that way. And so now this is a shell running inside that pod within the environment. I'll exit out. There's also a CLI that I can run locally to get a lot of this functionality on my host system directly from my laptop. Let me jump over and show you that CLI real quick. To install the CLI, they provide either a bash script that you can use, or you can use something like Homebrew to install it. I've already got it installed. And then the next piece is to get your Shipyard API token. And so in order to turn on the CLI for your account, you'll need to ask the team at Shipyard to do so. But once you do, you can go up here to the user and then click profile, and it will show up on that page. And you can grab that API key to use with the CLI. We can see here all the different functionality that we have. So I can do something like Shipyard get environments. That's going to list out all the environments that I have. And let's say I want to get the logs from one of my pods, like I could see from the web interface. I can do Shipyard logs. With the end flag, I can pass the UUID of that environment. And then with the service flag, I can tell it which service I want. So let's do API node. And we can see the logs coming out of my node-based API application. Similarly, we could port forward directly to one of those applications. So let me just port forward to that one. So instead of logs, I'll do port forward. And then my node application is listening on port 3000, so I'll do 3000. It wants the port flag. And now my localhost 3000 should be forwarded to that node-based API. And I can go here. And I'm connected directly to it. This would be super useful if I wanted to do something like maybe connect to my Postgres database directly with pgadmin or otherwise. I could port forward to that environment, make whatever changes I needed to. Let's say I was building out my base environment and I needed particular seed data and I wanted to run my migrations. I could do that manually once on my base environment, and then those changes would get snapshotted because they're in a named volume and built into my additional environments moving forward. So hopefully this gives you an idea of the power of ephemeral environments and the ease with which we were able to use the Shipyard platform to generate them. I created that base environment from my main branch, and now every PR that I create moving forward will get an ephemeral environment to validate before we deploy to staging or production. If you recall, we turned on the ability for Shipyard to populate information back on GitHub, so let's go see what it did on that PR. If I go under pull requests, demo Shipyard, we can see that the Shipyard app created this comment and tells us the environment was successfully built and running. We can access it at this link or see the build details at that link. And so this just makes it very easy for someone reviewing this pull request to now go check out what exactly these changes are and how they impacted the application. Hopefully that demo kind of gave you an idea of the power of ephemeral environments and why we would want to use them within our software lifecycle, and showcase the ease with which we were able to use the Shipyard platform to build those out for our project. At this point, we've got all the tools within our system to have a really nice developer experience with containers. And now let's shift gears and actually learn how to deploy them into the cloud. All right, congratulations. We've made it to the final module of the course, and that will be focused on deploying containers. So we now know how to build container images, run containers from those images. We've learned about how to do development with them. And now we need to build on those skills and learn how to deploy our containers to production. Now, one of the main benefits of containers is that they provide the standard interface upon which to run. As long as you can provide a container image that meets that open container spec, there are many cloud service providers that will happily take that container image and run it for you. I saw this article back in 2021 from Corey Quinn, who runs the Last Week in AWS newsletter, talking about the 17 different ways to run containers on AWS. Now, obviously, AWS is kind of this sprawling, massive cloud provider, but even still, to have 17 different ways to run containers, ranging from container-based serverless options like Lambda to Elastic Container Service to running Kubernetes with Elastic Kubernetes Engine. There's just so many different ways to run containers, and this is just within one cloud provider. And so that portability is both a blessing and a curse, meaning that it provides us this flexibility, but also it can be a bit overwhelming in terms of deciding which of these methods to use. And now, what do we actually care about when it comes to choosing a method to deploy our container-based workloads? I'd say the first item that's top of mind for me is security, and whether either the cloud provider is handling security out of the box and setting all those container runtime options such that it meets the threshold we need, or they give access to those knobs and dials that we can set them ourselves. The next one is the ergonomics or the developer experience. So how easy is it to go from having a set of container images and running those and getting traffic from the internet to them? Also, how easy is it to deploy new versions? So if I make a change to my code, how does that code make its way into production? And then the third one in terms of ergonomics is how do I work with the running containers? How do I check the logs? Can I monitor them? Can I collect traces easily? Combining those three elements make for either a good or bad developer experience when working with any of these platforms. The next one is scalability. So does the platform meet my needs in terms of the scale of any individual container or the number of total containers required? For example, can I access particular types of GPUs? What if I need to scale beyond the capability of a single host? Can I launch containers across multiple hosts, and how do those services then communicate with one another? Another key consideration is persistent storage. So we've talked about volumes within Docker. We've mostly focused from a developer perspective with Docker Desktop and seen how those volumes get stored on your laptop or desktop. However, if we're now running containers across multiple hosts and they're getting scheduled, and they could be scheduled on one versus the other, we need to think about how storage works and if it's possible for those storage to be accessed from different virtual machines or different physical machines. And the last one that I have here is cost. How affordable is it to run your containers in this particular environment? These range from sort of bare metal, where you're paying just for the compute but handling all the operations yourself, all the way up to maybe a fully managed platform as a service offering where they're charging you a premium for some of those improved ergonomics or developer experience features. So thinking about how much it's going to cost you, understanding the financial impact of your platform will be important if you're running a business based on these containerized workloads. Now, when I was planning out the course, I actually built out 3 different deployment targets. So one using Railway.app, one using Docker Swarm, and one using Kubernetes. Since we're already at about 4 hours into the course, I've decided to shift that slightly. Within this video, I'm going to demonstrate the Docker Swarm deployment, and then I'm going to create separate bonus videos showcasing how to deploy onto Railway and how to deploy onto Kubernetes for the sample application that we've been working with. And once those bonus videos are released, I'll have information in the description about how to access them. Now, at this point, you might be asking, why can't we just take the Docker Compose file that we created in Module 8, create a virtual machine, and run that directly? Now, while that would work, and you would have your containers running on that host, and you could set up the firewall to access them, it's not ideal. There's some major limitations with Docker Compose that prevent us from wanting to use that for a production workload. First, there's no way to deploy a new version of our containers without having to stop and then restart the container. And so by definition, you're going to have some downtime there. It might be very quick, on the order of a second or two, but nonetheless, you generally want to avoid downtime if you can. And then also, there's no utilities for easily rolling back a version with Docker Compose directly. Also, Docker Compose doesn't have a native way to handle credentials properly. We've been passing in that database URL or the Postgres password as an environment variable. There's no mechanism in Docker Compose to handle encrypted secrets. And so that's a major limitation there. Also, you can only run Docker Compose on a single host. So that hasn't been an issue as we've been developing on our development machines. However, we would like the ability to expand beyond a single host and add things like high availability in the future. And so Docker Compose is limited in that way. There's two other reasons you might have historically heard cited for not using Docker Compose in production. The first is that it used to not support health checks. And so we'll talk about what health checks are and add some in. That is no longer true. They've added health checks to Docker Compose relatively recently. And then the other one has also been mitigated, is that Docker Compose used to live as a separate binary when you would run it. And so it was just harder to install and config. Now that Docker space compose, rather than Docker dash compose, is built into the Docker binary itself, that's no longer an issue either. You may hear people reference these as potential reasons. Just know that historically they were reasons not to use Docker Compose in production. Now, I've phrased these as things that Docker Compose doesn't have. However, as we'll see, these are features that Docker Swarm does have built in. We can configure a deployment strategy to have zero downtime deployments. We can roll back changes if we want to. We can handle credentials via a feature called secrets, and we can scale a Docker Swarm cluster across many hosts. To keep things simple, I'm going to deploy a Swarm cluster on a single host. So it's going to be quite similar to conceptually to using Docker Compose up. We're going to create a Swarm cluster consisting of a single virtual machine, and then we're going to modify our Docker Compose file, and you'll see that the actual changes in the configuration are quite minimal. There's only a few things that we need to tweak to make our Compose file compatible with Swarm. We're going to deploy that, and then we'll set up DNS so that we can access it via the internet. What's the process going to look like? I'm going to create a virtual machine. I'm going to make sure that the firewall set up for that virtual machine allows inbound traffic on the necessary ports. We'll install Docker Engine, and so I'll use the script located at get.docker.com. I'm going to continue to use the Docker client running on my laptop, but connect to Docker Engine running on the virtual machine using this Docker host environment variable. So we'll connect over SSH and have the client running locally, but Docker Engine running remotely. We'll initialize the Swarm. We'll modify our Docker Compose file to add health checks. This allows Swarm to periodically ping our service and make sure it is healthy, and if not, replace it or restart it. We're going to add a deployment strategy, which allows us to deploy with zero downtime. And then we're going to add support for secrets so that we can handle the credentials for that database properly. Finally, we're going to build and push our container images to Docker Hub. Previously, we were using Docker Compose to also build our images. For a production-based setup, we want to have a specific image tag that we're running. And so I'll build and push those. And then finally, we'll deploy that stack onto the virtual machine and see it running. Now, at this point, I also want to issue a slight disclaimer about the way we've configured the database here. We're going to be deploying our database alongside the applications into our Docker Swarm cluster. Now, that's perfectly fine to do, and we do have a Docker volume to persist the data such that it will exist beyond container restarts. However, we're not implementing backups or anything like that. And so if you have an application where your user data is very important, you'll want to either implement a more robust setup that includes periodic backups and the ability to restore from those, or move the database to something like a database as a service from one of the cloud providers. Amazon has their RDS service, Google has Cloud SQL, etc. Okay, so I'm just going to create a virtual machine here on Civo. You can use whatever cloud provider you prefer. I'll call it Docker Course Swarm. We want one instance. I'm going to choose the small machine type. I'll use Ubuntu. Let's use the Ubuntu initial user. We can use the default network. We do want a public IP address. We will create a new firewall, and we use the SSH key that I have already uploaded to my Civo account. I'll click create. That will take a couple of minutes to spin up. Let's look at the firewall here. So right now it's using default. I just want to make sure that I have inbound traffic allowed on port 80. So I have this Docker test firewall that I created when setting things up. Let's look at the rules. So this is allowing inbound traffic on all ports. Let's actually turn that off. We do want to be able to SSH in on port 22. We're going to have web traffic coming in on either port 80 or 443. Let's also open up access for our two API ports. So in this case, it would be port 3000, and port 8080 for the Golang API, just so we can access those directly. Now let's go to our VM and attach this firewall to it. So instead of default, I want to attach it to Docker test. And now I want to install Docker Engine on this machine. So I will SSH into it. So we created that Ubuntu user. It should be using my SSH key that I already have set up. The first time connecting, you have to accept the fingerprint. And now we are connected to that machine. If I just try to run Docker, it doesn't exist. However, I know that there's this install script for Docker Engine here at get.docker.com. So I'm just going to do curl on that, pipe it to shell, and this will go off, and it has conditions within it to install for Ubuntu or Debian. And so this is an Ubuntu machine, and it should install properly. And so Docker is installed, but if I try to do something like Docker PS, I'm unable to connect to the Docker socket. I need to change the permissions of that socket to be accessible by my current user. And so I can do that with the chown command. And now if I do Docker PS, I'm able to access Docker. So I'm going to exit my SSH session. However, I can still connect to that remote Docker engine by using the Docker host environment variable. So I'll export Docker host, and in this case, it will be Ubuntu at that IP address. And now, even though I'm running this command Docker PS on my laptop, it's actually talking to the API of that remote Docker daemon. We want to enable swarm mode on that remote VM, so that's as easy as doing Docker swarm init. And we now have Swarm running on that remote host. Next up, we want to take our Docker Compose file that we created in module 8 and update it such that it is ready to go with Swarm. So I'll snag that Docker Compose file, copy it over into module 12. And so what are the modifications that we want to make here? We could just run this directly, like I was saying. However, there's a number of improvements that we want to make. So for a production-based system, and let me actually rename it. Instead of Docker Compose, let's call it Docker Swarm. YAML. There's a number of things we're going to do. First of all, we don't need our Vite-based front end because that was a development server anyways. So we'll just get rid of that entirely. Next up, we're not going to be managing the building of our container images via Swarm. So I can get rid of this build section. And instead, I created repositories on Docker Hub for each of my images. And I'm going to build and push those images to that. And so we can see here, I've got my Docker course API Golang, API Node, and client React Nginx. In order to build and push my images to those, I have this make target that is going to navigate to module 6 and then build version 5, 9, and 8 of the client, node, and Golang services respectively. And so that's effectively going to go into here, into each of these directories, and execute the build n and push n make targets. And so if I do that, this image that I'll be using for the front end will be sidpala/DevOps Directive Docker course, client React Nginx version 5. The API node, once again, will clear out the build portion and we'll specify to use the image, and this will be Docker course API node 9 was our final Docker file. And then the final one, API Golang, will be Golang number 8. Clear out the build. We're going to take inbound traffic on port 80 and forward that to 8080 because that was that unprivileged Nginx container running on 8080. We'll take traffic from 3000, forward to 3000, 8080 on the host, go to 8080 in the Golang container. Let's run this config file using Docker Swarm on that remote host. We already initialized the swarm. In this case, I need to update this IP address. So this was the IP address of the virtual machine I used when testing. Now I'm going to set it to the IP address of the one I just created. We've already initialized. I'm going to use this docker stack deploy command and then pass it the name of my swarm file. So I'll do make docker make swarm deploy stack. Because I didn't specify a compose file version in that file, I actually need to do that. And so at the top here, I'll specify that this is version 3.7. Let's try it again. And it's warning me that the Docker Compose option restart is not supported by Docker Swarm. And so I'm just going to remove those. It will handle restarting our services slightly differently. And the great thing about something like Docker Swarm is it's declarative. So now I can just redeploy the same stack over the top and it will reconfigure my services accordingly. Now if I do Docker PS, we can see the 4 containers that it's spinning up. And let me try to access them just at that IP address. So the IP address was 212. All right. And so I now have my containers running remotely on that virtual machine using Docker Swarm. However, there's still some improvements that we need to make, right? I talked about handling of credentials. Here, I'm still passing in those credentials via this environment variable. So we need to fix that by using a feature called secrets. And so generally you would create these secrets via some other process. So you wouldn't define it in your config directly because you don't want to store those credentials within your Git code base. And so I have a make target that we can use to create those secrets. It essentially uses the docker secret create command, pass it a name of the secret, and then here I'm echoing in the string that will get stored within that secret. So if I do docker secret list, there's no secrets currently, but then if I run this make target and run it again, docker secret ls, we now have these encrypted secrets living on that virtual machine that contain the information that we care about. So foo_bar_baz as our password, and then the URL string containing that information as well. Now, in order to consume those secrets, we're going to add another field here at the bottom called secrets. The first one is database URL, and we're going to say external true. And what external true is saying is that we created this secret already and Docker Swarm doesn't need to manage it as a part of this stack. We'll do the same for Postgres password, external true. Great. And so now that we've told Docker Swarm about those secrets, we need to tell the services that are consuming them to do so. And so what I'll do here is we can tell this database service that we want to consume the Postgres password. We no longer need the Postgres password here. I will change it. I will specify the Postgres user to be Postgres. So the way that secrets get consumed is as a file mounted into the file system using a temporary mount structure where that file only exists in memory. And so I needed to adjust my application slightly, whereas previously they were expecting to read those values from an environment variable. Now I'm expecting to read them from a file. And so I need to tell the application where that file lives. And so in this case, that file will get mounted in to this location, basically under /run/secrets and then the name of the secret. And so I'm going to tell my application, this is where you should go look and read in that password from the file. Similarly, we will have for our APIs, something very similar. So we're telling it the path to the file where that secret's going to be mounted in. In this case, this will be database URL. And there we go. And then let me just show you real quick the modification that I made to the application so that it can either read those secrets as environment variables or as files. So if we go to our Node.js application, here, source, database. And so when I'm populating this database URL variable, I either load it from the environment, or if that doesn't exist, then I read from the file system at this path that I'm passing it. Very similar on the Golang side, where when I'm initializing, I either get the database URL directly, or if it's empty, then I'll read the file and use that instead. And so now I can redeploy using those secrets. Now also, it takes my swarm config file and turns that into a stack with many services in it. So I can do make swarm ls, and that's going to list the different services. And we see that we have our different replicas here, and they all appear to be running except for the Golang one. Let's reload our application. And so it looks like our front end is still working, but our APIs may not be. So if I navigate to, and so let's take a look at the logs for those containers to see what might be going on. Let's look at the Node API logs. It looks like we are refusing to connect. So within the Node container, I can print the environment. I can see that we have this database URL file. That looks good. What happens if I cat that file out? Let's see. Okay, so it looks like when I tried to use this -n option for the echo command to avoid new lines, it actually included that in my secret file, which is what I didn't want to happen. And so I'm actually going to remove my stack, make swarm remove stack. So it looks like the -n I was using to remove the new line at the end of the file was actually getting included in the secret. So I'm just going to use printf instead. Do make create secrets. And now let me redeploy my stack. Let me make sure that the secret looks okay within those containers. So in this case, let's cat this out within the Postgres container. That looks good. And then within, let's say, the Golang container, or no, we'll do it within the Node container because the Golang wouldn't have cat within it. Okay, so that looks much better. And now, do my services look healthy? they do. And if I go to my IP address and refresh, I can now access my application again. Okay, so minor detour there. How I was creating those secrets, there was an issue with that -n was making its way into the secret itself. And so I fixed that by using printf, and now the secrets appear to be working properly. Now, the next thing that I wanted to do is to add an ability to deploy new versions without bringing down the old version first. And so for that, we actually use the deploy configuration option. And so for our front end, we will add a deploy section. And within this section, there's a few things we'll add. We'll put it on replicated mode with a single replica. So we could change this to 10 and it would spin up 10 copies of our front end, but we just need one for now. And then the key configuration here is update config. We want to start the new container before we terminate the old container. So that's what this order says. You can actually do stop first if you want to do the reverse. And so this is this deploy configuration is how you tell Docker Swarm how you want to do rolling updates. We'll have pretty much the same configuration for our other services as well. Let's make the Golang application have 2 replicas just to show how easy that is to do. And then the final piece of the puzzle that we wanted to add is health checks. And so we want to have a way for Docker Swarm to know whether our container is ready or not, so that when it's checking, should I bring down the old container? Is the new one ready to accept traffic? The way that we do that is via health checks. Now, the health check config is relatively straightforward. You use the health check key, you give it a test, and in this case, we're saying run this command inside of that container. So it's going to try and curl localhost 8080. And then I've configured my Nginx configuration so that when you hit the /ping route, it will just return Pong. You then tell it how frequently you want to issue this health check, how long you want to wait before you consider it to be timed out, and how many tries before you consider it to be a failure. Finally, the start period is how long you expect it to take before the container is ready from initial boot up, before it needs to do this test. In this case, our container image already had curl built in, so there was no additional changes to the application that we needed to make. For the API node service, we'll have a very similar health check. I'll add it right here. In this case, though, we don't have curl installed into our container image. We wanted to keep our container image as minimal as possible. We didn't want to have extra utilities floating around. And so in this case, I actually defined a health check in JavaScript that's going to be run from within the container and tell us if the container is healthy or not. I'll show you what that looks like. So under API node, under health check, we're using the HTTP package. We say take at up to 2 seconds to ping the /ping route on port 3000. If we get back a 200 code, great. If we don't, then fail. And so this is what is getting run by that health check inside the container every 30 seconds. For Golang, it will be almost identical. In this case, I have a separate binary that gets compiled in my container image. And so if I look at the application, I have this health check package. Within here, again, I'm just pinging localhost on the route ping. I have that defined in my application to return a 200. And then in my Docker file, when I'm building my application, I build both my health check as well as my main.go. And so these are 2 separate binaries that live in my container image, one of which is the application, the other one gets run by this health check. Okay, so with those health checks defined, I can now redeploy my Swarm stack. And now I can list out those services. We'll see something interesting though. If I do a Docker PS, We now see under the status field, see that these have a status of starting, meaning that it's using that health check to determine whether or not the container is healthy or not. And until it is, it won't route traffic to those containers, and it keeps the previous containers alive such that they can continue to receive traffic. Now that those health checks have started passing, we can see that they've been up and they are now healthy. And so we should be able to continue to access our application with no downtime. And so now whenever we make a change, we would build and push that container image, update our Docker Swarm configuration if needed, redeploy, and Docker Swarm would be intelligent enough to use those health checks to determine when we can route traffic to the new containers or not. You'll also see that because I have 2 replicas specified in my config, we get 2 containers both running that Golang image. A couple of other additions that we could do, we could configure our Nginx front end to retrieve a certificate from Let's Encrypt, for example, and store that in a volume such that it can persist across container restarts. Because right now we're serving traffic on port 80 over HTTP unencrypted. If we go to HTTPS, we're not serving on 443, so that doesn't exist. We also can update our DNS settings for a domain of our choosing. And so, for example, we can go to Cloudflare under DevOps directive. I already have this set up, but I'll update it to be the new IP address. And so we can update this. And that will take a few minutes to propagate, but because I already had the old one set up, we can just navigate to it directly. And as you can see, we're now routing traffic from that domain to our virtual machine, hitting our application, running within Docker Swarm, and everything's behaving as expected. You'll also notice that here I do have HTTPS. And now this is a bit of a hack because it's using Cloudflare's flexible TLS. And so I have this set up such that encrypted traffic goes to Cloudflare. That's where it terminates TLS. And then it sends that request unencrypted to the origin server. And so if you're not dealing with particularly sensitive information, depending on your threat model, this may be sufficient. However, if you are dealing with sensitive information or there's requirements about the data that you're handling, you would want to terminate TLS on your system. This can be done, like I was saying, you could have Nginx go off and get a Let's Encrypt certificate at its first startup. You can also handle that kind of at the ingress layer for your Docker Swarm cluster using something like traffic or another ingress controller that can handle that. And so with that, we have our application deployed to a virtual machine running in the cloud, being managed by Docker Swarm. We've set it up to use secrets to handle the credentials properly, use health checks to allow us to have 0 downtime deployments. And so that's great for a single node. If you want to add high availability to your system or deploy to multiple nodes, it starts to get a bit more complex, especially around how it manages volume. So in this case, we have a single volume for our Postgres data on that virtual machine. If we wanted to have a multi-node cluster, we would need to look at volume plugins and how to manage those, how to allow Docker Swarm to manage those across multiple hosts. And so I didn't want to go into that level of depth in this course. If you do want to dive a bit deeper on Docker Swarm, there's a great course from Brett Fisher called Docker Swarm Mastery that I would suggest you take a look at. That'll be a full deep dive on how to use Swarm. There's a recent reinvigoration of excitement around Swarm. They just added support for what's known as the CSI, Container Storage Interface, which is a standard interface for managing persistent storage that is used in Kubernetes. It has a lot of usage and maturity from that domain that's now going to get pulled, hopefully, back into Swarm and make it a viable option for production deployments moving forward. As I mentioned, this is just one of many, many different options for deploying containers. Hopefully, this gives you some ideas, but do be on the lookout for the bonus content around how to use something like Railway or Kubernetes to deploy the same sample application. And with that, we've reached the end of the course. Congratulations. Hopefully, you feel ready to go off and incorporate containers into your software development and deployment approaches and use the lessons you've learned to improve the software systems within your organization. To recap everything that we've covered, we started with some fundamentals, exploring why we should even care about containers in the first place, how the evolution of virtualization brought us the current state of containers, the underlying technologies within Linux that enable containers to work, and how Docker fits into the picture. With that as our base, we were then able to move on to learn how to use containers. We used public third-party containers for things like databases and interactive test environments. We built out a multi-service web application, containerized it, established a nice development workflow, and then finally deployed our application to the cloud. I hope that you enjoyed taking this course as much as I enjoyed making it. Also, if you'd like to join a community of other DevOps practitioners, I run a Discord server with lots of amazing folks where we talk about this type of thing all the time and answer each other's questions. There's a link in the description if you'd like to join. If you want more DevOps and Docker content, YouTube should be recommending another video over there. That's it for this course, and remember, just keep building.